Okay, we are going to get started because we have a lot of material. So hopefully, if you're in this room, you're here for the introduction tutorial. Our goal today is to expose you to as many different topics so that you have kind of a wide understanding of different things that can go on within the OHDSI community. I will admit, secretly, the faculty and I have a secret mission by exposing you to all these things. We want to expose you to hopefully something you get excited about. And at the end of the day, we're going to talk about joining the community, and we hope that whatever you're excited about, that you take the action to potentially join if you want to. So like I said, our goals for today are to expose you to in the community of how we go all the way from data to generating evidence. So over the next few hours, we're going to show you the OHDSI approach to do that, and we have tools, we have best practices, and we do this in an open source way. Our goal is that you have a solid understanding of potential ways that members of the community both contribute and receive value from the OHDSI community. So you don't have to think about this as the only way that you can participate in OHDSI is by doing something and being part of our working group. You could also just receive value like, I have a data set, I want to get it analyzed, I'm going to reach out to the community to figure out what's the best way to get this done. I'm going to start by introducing our faculty. First, I'm going to thank them for spending time not only preparing for today, but also being here to help present and answer questions. So everybody has such a great bio. I have to read it off the paper. So I'm going to start with Roger Carlson. Roger is a senior analytics engineer at Corewell Health Research Institute, a division of Corewell Health. I actually have known Roger for a couple years now. I met him, there was an NIH project called All of Us, where data partners were converting their data into the OMOP Common Data Model. And what Roger's very well known for is his work in specifically helping Epic data partners convert their data to the OMOP Common Data Model. So he's done a lot of work in that area. Yong Chen is a professor of biostatistics and founding director of the Center for Health AI and Synthesis of Evidence, otherwise known as CHASE, at the University of Pennsylvania. He also directs Penn Computing, Inference, and Learning, focusing on clinical evidence generation, causal AI, and evidence synthesis. He has published more than 260 peer-reviewed papers, so now I know I have a lot of work to do. Presenting today with Yong is Jason. Jason is an assistant professor at the Division of Public Health Sciences at Washington State University in St. Louis. Jason, his research interests include focus on statistical methodology on data integration, including cancer multi-omics data, meta-analysis, and federated learning on real-world data. He is also interested in cancer surveillance and disparity, vaccine and pharmacovigilance, and mental health. Together, Yong and Jason are going to present the topic of our methods that we apply to real-world data. Next is Katy Sadowski. She is at Boehringer Ingelheim. I did it, okay. That's a hard company name to say. Katy is very active in the open source development community. Specifically, I want to highlight that she maintains the data quality dashboard tool, which we probably are going to hear later in your presentation, Katy, so you'll learn a little bit more about that. She also maintains a DBT Cynthia, which is like an OMOP ETL demo package that you could learn from. But she's also a member of the HADES work group as well as the clinical trials work group. The HADES work group is going to be really important later today, and she'll be talking to you about that as well. Nicole Pratt is here. She is a biostatistician and a deputy director of the Quality Use of Medicines and Pharmacy Research Center, all the way from the University of South Australia. She is the president of the OHDSI Australian chapter and lead of the Australian Health Data Evidence Network, or ARDN. Did I say it right? Okay. Nicole is a chief investigator on the Center of Research Excellence on Medicines Intelligence and a member of the Drug Utilization Subcommittee of the Australian Government Department of Health, Pharmaceutical Benefits and Advisory Committee. Nicole is going to be talking about, once we've used our standardized tools and applied our standardized methods, how do we actually interpret the clinical evidence that comes out? And last, my name is Erica Voss. I work for Johnson & Johnson. My background is primarily in data warehousing, but I got really excited about observational data about 15 years ago. I spent the early part of my career doing conversions to the OMOP Common Data Model, but now my team focuses on producing evidence from our observational data set specifically for safety-related reasons. So epidemiology focuses on safety within Johnson & Johnson. A little housekeeping. Hopefully everybody in here has a badge. If you do not, I need you at some point to go receive your badge for today. I want everybody to be aware we are recording today's session. Every time we do these tutorials, they're all on YouTube. That is important because we encourage you to ask questions, but we do have, there's a mic, and when you ask your questions, we want to make sure that you have the mic so that the YouTube audience, future YouTubers will hear what you have asked. And also very important, where is the restroom? If you just go out, and right outside the rooms, there are the men's and women's restrooms. Okay, how is this day gonna look? So we're trying to cram a lot in before lunch, and it's very important that we get out on time for lunch, so we will work through this agenda. I'm gonna give a little bit of an introduction for today, and then we will hand it over to Roger, who's gonna talk about community data standards, specifically the OMOP Common Data Model and the OHDSI vocabularies. Next, we'll turn it over to Yong and Jason, who are gonna talk about our methodologies, specifically doing characterization, estimation, and prediction. And this year, actually, they're going to talk a little bit also about federated learning, which is becoming a critical component within the OHDSI community. Then we'll take a short break. And when we come back from the break, Katy's going to talk about our open source analytics, so our key packages, as well as our approach to doing that. From there, Nicole is going to then talk about clinical applications of network studies. So hopefully, and I know because everybody's great students in this room, you all did your homework, and so Nicole's going to go into detail about the results of that specific study. And then, like I said, we have our secret agenda. We hope that you want to participate in the community. At the end, I'm going to tell you how you can do that and how easy it is to participate if you want to. So let's get into the introduction. So this class is for new people. So if you are new, OHDSI stands for Observational Health, Data Sciences, and Informatics. And we were founded in 2014. Our central coordinating center is Columbia University. And it's very important to stress that this is a multi-stakeholder, interdisciplinary, open source collaborative. And what that means is that we're not just looking for physicians. We're not looking just for data analysts. It's anybody who has interest in gaining value from real-world evidence. We need to bring all these different skills together in order to do this type of work. So throughout today, you're going to hear a lot of different things. No one person in this community can do all these things. People kind of pick their area of expertise and kind of contribute in that way. So do not worry. You do not need to be a statistician and a data analyst and a clinician to do this work. You can kind of pick the piece that you want to focus on, and that's a great way to contribute. The OHDSI mission is to improve health by empowering a community to collaboratively generate the evidence that promotes better health decisions and better care. Our vision is a world in which observational research produces a comprehensive understanding of health and disease. Every year we produce this slide because every year we get a little bit bigger. And so this year we have 4,751 collaborators all around the world. Across 88 countries in 21 time zones on 6 continents, and we're all one community. And I think Craig is very proud of that we have 9,000 LinkedIn followers. Now, we are the OHDSI community, but you're probably going to hear the word OMOP come up a few times today. For example, like we still call the CDM the OMOP CDM. But let me tell you a little bit about what that is. OMOP was the Observational Medical Outcomes Partnership. And this was a public-private partnership in the US, and it was a project that was specifically focused on how can we better use observational data to understand the effects of medical products. It was a 5-year project, and I would say one of the centerpieces that came out of that project was the OMOP Common Data Model. And so the project completed, but all the scientists that were involved were really still excited about the work, and they wanted to continue. But also, they didn't want to continue within the bounds of just having the narrow focus of only studying effects of medical products. And that was really kind of the birth of OHDSI from there, moving on from OMOP. Okay, again, we're all great students, so we all read the paper, but I'm going to do a little bit of a teaser up front to make sure that we're on the same page in terms of like terminology and things that are going on within this paper. So this is the risk of aortic aneurysm or dissection following use of fluoroquinolones. And if I were to kind of summarize this paper to its key main idea, this paper is looking to understand specifically for fluoroquinolone use, which is an antibiotic that's typically used to treat UTI, there was concern from some studies that taking fluoroquinolones could increase your risk of aortic aneurysm or dissection. So we're going to use this paper as a theme throughout today's presentation, so it's good to at least know what these 3 key ideas are. So let's define these ideas. So fluoroquinolones, these are antibiotics. Most likely in your life, you've probably been exposed to one of these antibiotics. They're very, very common if you have a cold or a UTI or something more serious like anthrax, you might be exposed to these. So you've probably heard the name ciprofloxacin or Cipro for short. Maybe you've heard of levofloxacin. Very, very common. And these are well-tolerated drugs with rare outcomes of hepatotoxicity. Usually what happens when people take these medications is they get an upset stomach, they might have a headache, they might get a rash. There are some severe risks like QT prolongation, seizures, tendon rupture, and photosensitivity. So this is the main drug that we are asking our question, or the main class of drugs that we're asking our question about. Probably most people in this room know what a UTI is, and probably most of you have actually had a UTI. This is an infection of the urinary tract, often caused by bacteria that are on the skin or in the rectum. If you're so lucky that you have not had a UTI in your life, usually you have like a burning sensation when you pee. There might be blood in your urine. And if it's really bad, you'll have some fever and chills. You might have some back and side pain, nausea and vomiting. And when I was preparing for this presentation, and I was reading the risk factors, the number 1 risk factor is just being a woman, so there's that. But you can also increase your risk if you've had prior UTIs, depending on your sexual activity, and things like poor hygiene. And you get diagnosed in your outpatient doctor. You probably pee in a cup, and you can diagnose UTI. But we treat this with antibiotics. Now, what I had to learn a little bit more about is this outcome that we're interested in. So what is aortic aneurysms and aortic dissection? So aortic aneurysms is this idea when the aortic wall kind of bulges out. And you can see this picture that I have on the screen with the heart. You can kind of see that the heart is bulging. We don't want that. That's not good. That's the aortic aneurysm. And an aortic dissection is when you have a tear in the aortic enema, and there's like intimum, and then the blood can actually split the layers and form this false lumen. That's the second picture. You can kind of see like the blood has found a little path outside of the aortic wall. These are both bad things. We don't want these. They're rare, but they can be fatal. So the idea behind this paper is that we want to understand, does a common drug like fluoroquinolones that you would take for a common thing like UTI cause this increased risk? We need to understand this. Now, within OHDSI, we have this analogy where we talk about what we do within the community is we kind of essentially build the building blocks to help answer these things. So the building blocks in this study are there are databases, we have phenotypes, we have a study design, we use best methods, and we have standardized tools. So in the study, there are 14 databases. They're all been converted to the OMOP Common Data Model. That's what allows us to do this work. Roger today is going to talk about what does it mean to be standardized to the OMOP Common Data Model. Next, you need phenotypes. So you'll hear kind of phenotypes, cohorts used interchangeably. It's this idea that we have an algorithm that's able to find a specific set of individuals. So for example, we'll need a phenotype that finds people who are exposed to fluoroquinolones. Now, today we're going to talk about phenotypes and cohorts, but we're actually not going to go into detail about how to build a phenotype. If you are interested, there's a working group session on Thursday where you can learn a little bit more. And there's tons of opportunities within the community about doing phenotypes. So there's plenty of ways to get involved and learn more. Next is the study design. So even when we perform these studies, we do them in a standardized way. Specifically, this study is something we call an estimation study. And so typically when we ask estimation questions, they go a little something like this. Does exposure to, in this case fluoroquinolones, have a different risk of experiencing some outcome? In this case, it's aortic aneurysms, aortic dissection, within a given time frame. This case is 60 days, relative to some type of comparator treatment. And the paper talks about the comparators that are used to treat UTIs, but they're just different medications. Nicole is going to talk a little bit more about the specific study design in her part of the talk when she's actually going through the results of the paper. Next, we have methods, and this, like I said, this is an estimation study. So Yong and Jason are not only going to talk about doing estimation studies, but also we do characterization and prediction. And last but not least, Katy's going to talk about once we have standardized methods and we can assume a standardized data model, we can then develop tools to implement those methods on our standardized data. So Katy's going to talk about important tools like Atlas, our OHDSI methodology, as well as strategists for implementing some of these methodologies. And again, going back to our building block analogy, the idea is if you can kind of break up a study into these individual components, once you build out those components for your study, it actually becomes fairly easy to generate evidence and feel that it's reliable and standardized. Okay, so that's our quick introduction to OHDSI. I'm now going to turn it to Roger, who's going to talk through our data standards.
Okay, thanks, Erica. By show of hands, how many people are here for the first time? And I mean in this intro class. Ooh, good number. By inference, then, the rest of you have been here once before, so you're probably still trying to learn something. Personally, as Erica said, 7 years ago, I sat in a hotel room very much like this, in a different city, in a different hotel, but they're all pretty much the same. And I heard about the OMOP CDM for the very first time. So now 7 years later, I'm teaching this. So if you find yourself overwhelmed this week with all of the information that you're going to get, not just here, but later on, just know that it does eventually make sense, and it does eventually makes sense. If you want to know more, I would encourage you to join our working groups, the OHDSI working groups. You don't have to be an expert to join a working group. I was kind of afraid at the beginning that this is a working group, so you have to know what you're doing, and you don't really. You can just go and you can listen and get information. I joined the CDM group, I joined the vocabularies group, I joined the Themis group, I joined the hospital systems group, I even joined the oncology group for a while, and I finally kind of dropped out of some of them because you can't swallow the ocean. But they're very friendly. You can ask naive questions, and nobody's going to put you down. So that's what I would suggest to help digest some of this stuff. So anyway, okay. So I think we all know that real-world data is a mess. There are electronic health records, pharmacy systems, surveys, registries. In addition to that, there's all kinds of different data, structured, unstructured data, imaging data, claims data, genomics. And in addition to all of that, all of those can vary by countries, languages, regions, companies. So the purpose of OMOP is to give some sort of standardization to this. I like this slide because I think Christian used it in the first intro class that I went, so it has been around a long time. But an analytical method, it's kind of like an appliance. It's the same everywhere. It's got the same function everywhere. It's used the same everywhere. But depending on the region or what country, you may not be able to use it. They all have different interfaces. And I've done this for 30 years. Trying to share data with another company, you have to write new SQL. I mean, you can't just use some SQL that you've used before. You might have to agree on standards, have different file specs, and whatever you're doing, it's a one-off. You can't really use it again. And so, each study or each time that you're sharing data, it's a brand new thing, and it can be like those wires there. And there's downsides to it too, because you have to rely on the partner to be able to do this. They may not be as sophisticated as you are, or vice versa. It's not scalable, it's not transparent, it's expensive. And so OHDSI decided to cut through some of that and give the same interface for every region, every vocabulary, every source data system. Excuse me. And that allows then tools to be created that will work against this standard. Standard SQL will work. Katy's going to talk about some of the other tools, Hades and Atlas. So that gives us that's kind of the reason for OMOP. Another example is suppose there are two hospitals, Hospital A and Hospital B, and they want to compare their use of ciprofloxacin. I've been calling it ciprofloxacin in my head all this time, and now I find out it's not how it's pronounced. Anyway, Cipro. So Hospital A Hospital A uses RxNorm in their coding, and Hospital B uses HEMOC, a different coding system. So in Hospital A, the code for Cipro is 2551, and in Hospital B it's 104. But because they are both part of the OMOP, they both have an OMOP model, they have converted their data to the OMOP standard, which is 1797513. So they both convert it to that number, and then they can share the data. And so that you can see, good. All of these records have the same standard concept ID, even though they have different source concepts or source codes. So OMOP was built around a number of principles. First of all, it is patient-centric, and so that means that everything is about and for the patient. As Christian likes to say, this is not a system to run your billing or to run your insurance company. It's specifically for observational research because it's the people that are important. Another principle is that they have a standard vocabulary and a standard data model, which we're talking about today. The concepts are domain-oriented. It accommodates data from various sources. It preserves data provenance and source data. So even when you're putting your OMOP code, your standard concept, you still put your source code in there so that you can go back and look at your source system to make sure you're not losing granularity. And then it's extendable and evolving. It's what we're doing here every year and what they do in the work groups. And it's database independent. So the standard OMOP tables, these are also grouped into the standardized vocabularies, standard clinical data, healthcare data, and health economic. I'm going to go through those here. The standardized vocabularies are the heart of OMOP and what makes it so unique. These tables contain information about all of the concepts in the CDM, and all of this data is provided by OHDSI. You don't have to do anything. You know, all 12 million concepts that are in 142 vocabularies, that's that onion iron adapter that has 142 plugs in it. Separated into 44 domains, over 80 million concept relationships, ancestral relationships, and concept synonyms. So they've gone to done a huge amount of work to provide this information for free to anybody who wants to download it. The standardized concepts are here in the middle in red. Concept table, vocabulary, domain, concept class, concept relationship, concept ancestor. There is one funny little one down near the bottom called source to concept map. That one does not come with any data in it, and we'll talk about what that's for later on. But these are all pre-filled. And I've got a link here. If you can download the stack, there is a link here and I'm not going to go to it. General structure, download, and use, which shows you how to download the vocabularies, what to do once you've downloaded them to load them into your tables. And there's good instructions there. Just where do you get the vocabularies? There is a product, it's a web-based product called Athena. It's athena.ohdsi.org. And this is a tool, has a couple of uses. The one we're talking about right now is to download your vocabulary. So if you come and you click the download button, or the download tab, it will bring you to this screen. And over here, you can check the codes that you want to download. I suggest downloading as many of them as you can. It doesn't really hurt anything to have codes that you don't use, but sometimes it might come up that you need to have a code, a vocabulary that you didn't know you needed. There are some exceptions. Some of them are licensed, so you actually have to have a license in order to get it. And there's some others like veterinary vocabularies that you're probably not going to use unless you're a veterinarian. So anyway, you check all of those, the ones you want, and they're like 142 is what I said. So, there's a lot of them. And then you just click the download vocabularies. It'll think for a while. And what it does is it creates a unique vocabulary set for you, whichever ones you have checked, and it will create the concept table, the concept relationship table, build it all, and then it will send you a link that you can download. You go to that link, download a zip file, extract it, and then you can load those CSVs into your vocabulary tables. So that's a bit of an overview, but that link in the last slide has more. So that's the vocabularies. The next group of tables is the standard clinical tables. Again, since this is person-centric, it's the main table in it is the person. These tables contain the information about a person. And this is not filled by OHDSI. This is what you have to fill in your ETL. And so each person can have one or more visits, or none visits, I should say 0 or more visits. A person may have 0 or more conditions, drugs, procedures, devices, measurements, observations, notes. These are the domains that I was talking about. And so this is the data that you put in there, but you do use the standardized vocabularies. You join your source data to the standard vocabularies to fill that into the standard clinical tables. The last group, healthcare and economic tables, are very important, but not quite so important for this particular introductory class. But these have to do, these tables have to do with various kinds of reporting and internally for the tools to use. So I am mostly going to concentrate on the vocabularies tables. For the clinical data tables, Claire will be doing a tutorial this afternoon on ETL. That would be a good one to go to. So the overall flow is that you've got your source data. Mine happens to be Epic Clarity. It could be, Cerner, or it could be surveys or oncology data if you've got an oncology database. Anyway, your source data flows through the standardized vocabularies. So you join your source data to the vocabularies to get the standard concept IDs, and that information goes into the standard tables, clinical tables. And then the other standard tables off to the right there are get filled through other processes, but that's the main flow of the thing. For those of you who love entity relationship diagrams, as I do, there is on the website a complete ERD. We actually, a couple of years ago, we had a contest that I entered and lost, but Martine came up with this one, and this was deemed the best one. It is impossible to read here, but if you go to the link, you can zoom in and you can see how the tables are, joined and on what fields. So that's a fun thing. I just thought I'd show you that it's available. All the links in this presentation are live, so if you get a copy of the deck, you can click them and go to this additional information. Okay, so we've done our real world, we've talked about principles, and we talked about our standard tables. Now we need to talk about source codes, concepts, and mapping them. Just definitionally, I want to separate a concept ID versus a concept code. In OMOP, a concept ID is always a concept in the concept table that has an ID that is unique. It is a unique artificial key throughout OHDSI. So every one of those 12 million concepts that I talked about has a unique concept ID. Concept codes are those that are assigned by an entity, like Loink or SNOMED, something like that. And any particular concept code in the concept table could have multiple meanings, depending on its context. And some of the contexts are vocabulary, domain, and concept class. And there's links to explaining what those are. But let me show you with an example. For instance, ciprofloxacin has an RX norm code of 2551. So if you go to the concept table and you just query for that code, you're going to come up with 3 records. And these records, 2 of them are drugs, but different drugs, and one of them is a measurement. So just that number itself doesn't do you any good. The context for this, however, is we want the RX norm version of it. And so adding to our query, we say if the vocabulary is RX norm, then we come up with ciprofloxacin. Yeah, it does that every day. Page up. And so we got 1,797,513. I'm not going to try to do that again. So you've got a 1.7 million number. So that's the concept ID for floxacin, ciprofloxacin. There's also a concept name field in the concept table, and if you just try to, so the same works for the concept name. If you just try to query for aortic aneurysm, you're going to get a whole bunch of different records. One of them's a drug somehow, and the rest of them are conditions, but these conditions have come from different vocabularies. And so you have to add the context. But even adding the context of conditions, SNOMED, and disorder, you still get two records. And that's because one of these records is a standard concept, the other is not. And we're going to talk about standards. So I want the standard concept. I choose SNOMED and a standard, and I come with 317585 for that, aortic aneurysm. So different categories. There are non-standard concepts. These are usually representations of the source code. There are standard concepts, which those non-standard concepts are mapped to. And then we have classification concepts. These are used in hierarchies, mostly used for reporting. And I'm going to talk about hierarchies near the end. So your source codes can come from a variety of sources. There may be international terminology systems like SNOMED or LOINC. There may come from a country-specific type terminology like READ from England and ICD-10-CM from the United States. There may be free text strings, which is the bane of your existence. You'll spend a lot of time on free text strings, like units, milliliters per second. They can be spelled differently. You can get, like some tests have a string value, like, negative. You tested negative for something. Or it could be neg, or it could be negative without the A, or just because whatever they type in. And so the last one may come from your specific system. Epic has procedure codes that the hospitals can make up. So L111 could be, even if somebody else has the same Epic system, they may not have those codes because they allowed you to make up your own procedure codes. So those are the sources for them. Non-standard codes have to be mapped to standard codes in order to be any use for sharing the data. So that just has to be that. It just has to be that way. But you have some options for doing it. Established code mappings, some of them are standard, like SNOMED and LOINC, and some of them are non-standard, like ICD-10-CM. If these terminologies are non-standard, they have to be mapped to standard codes. So if I have an ICD-10-CM, I cannot just put the concept ID for that. There is a concept ID. OHDSI went and made a concept ID for that, but that's not the one I can put in my data. I have to map that to the SNOMED code. And to do that, I join the concept table to the concept relationships table. So as an example, if I want I71.9, which happens to be aortic aneurysm, I can pull that out and I get a concept ID of a 35 million concept ID. But you'll notice here under standard concept, it's null. So it is not a standard concept. So that number won't work in my code. So I can take that number and put it into a second query on the joining the concept relationship table with the relationship of maps to, because the relationship table will define what the relationships are, and it will come up with the number I want, 317585. But you don't have to do that in 2 steps. You can do this all in one set of code. I end up using this code in every one of my modules because it works everywhere. All I have to do is change the variables in here. So I've got ICD-10, the domain is condition. I want the maps to relationship, maps to a standard code that is also in the condition domain. And I71.9 goes directly to 317585. So this is very, very useful code. And another reason why it is very useful is I can use this same code for procedures. All I have to do is change the variables. I'll call it this. I want a CPT4 code for the procedures, map to a standard procedure, and 0058T will map directly to that 4 million number. Now, the one that's going to, as I said, be the bane of your existence is proprietary code mappings. There are 2 methods within OHDSI. One is more of a basic method, one is more of advanced. The source to concept table method was developed earlier. It's still being used. It is a way to map your proprietary concepts to a standard code, and so that means you have to do it. Fortunately, there's not a lot of them because most everything you're going to do will be from standard vocabularies, but these, especially units and string values from tests, that sort of thing, you have to do. For the source to concept map table, OHDSI has a standard tool called USAGI that you can use to, it helps you to figure out how to map your codes. A lot of people that I have talked to just use Atlas, but USAGI is a helpful tool that will help you fill the concept, source to concept map table. I've got a link there to the book of OHDSI. The extract, transform, load section. Claire is going to talk, I believe, more about this in the ETL, so you got something to look for there. The other way to do it is using the concept and concept relationship table, just like all the standard concepts have. The only problem is you have to make up your own codes. You have to make up a concept ID. The key to it is that it has to be over 1 billion, or it has to be over 2 billion. So sometimes these codes are called the 2 billionaires. So you will create a record in the concept table that's over 2 billion, and then you also create another record in the concept relationship table that maps that concept that you made up to a standard concept. And there is a wonderful article called Custom Concepts by Maxine. Is that Monet or Monet? Okay. And the Themis work group that tells you exactly how to do that and what values you have to put where, and it's an extremely useful tool. So let me give you a couple of examples. If let's say we have already done USAGI and queried the source to concept map. If I want to query a particular source code like milliliters per second, I have to, in doing this, I also have to make up my own vocabulary, so I called it SH unit, because at the time, Corewell Health was Spectrum Health, and I haven't bothered to go and change all the unit names. And so you can see that milliliters per second in my SH unit does go to the 44 million that we had found before. So that's how you can in your ETL you can find it. In the concept relationship table, again, if I just query SH unit and milliliters per second, I will come up with this is my 2 billion concept ID. So we know that I have created it, or we have created it. And then to find out what it maps to in a standard concept, I can put that code into the concept relationship table query, and I come up with the 44 million concept ID that we were talking about before. But another piece of good news is that, remember this code that we had before? This also works for your proprietary codes, because all I have to do is put in my made-up vocabulary. The domain is unit. It maps to a standard concept, also a unit, and it comes up with the 44 million number. So we've talked about standards and OMOP principles, the standard tables, concepts and mappings, and now we're going to talk about hierarchy, because concepts can have ancestors and descendants. So this is a representation of the ancestry of aortic aneurysm. So aortic aneurysm can have ancestors. It can be, one of its ancestors can be an aneurysm of the artery of the trunk. It's not to say it's its only ancestor. There's also aneurysm of the artery or peripheral artery. So this one tree, it does not represent everything, just this is one tree in there, okay. Aneurysm artery of the trunk is also an arterial aneurysm, which is also an aneurysm, which is also a disorder of the cardiovascular system. So you've got more and more levels of separation. This becomes important later on when you're trying to create concept sets. An aortic aneurysm also has descendants, so it could be an aneurysm of the descending order or of the thoracic aorta. You might want to, hone in on just a particular type of aneurysm, aortic aneurysm. So this is just an example. For those of you who like code, who like SQL as I do, this can be queried directly from the concept and the concept ancestor table. That's where this one comes in. So if I'm looking for all of the ancestors, I want to use the descendant concept ID. 317585 was our aortic aneurysm, and sure enough, there's aortic aneurysm, and it has an ancestor of aneurysm of the artery of the trunk, and so on and so forth. You can see all of its ancestors and all the different trees when you do it like this. And descendants also, an aortic aneurysm. There's aneurysm of the aorta, aneurysm of descending aorta, and that sort of thing. So you can have all of those. So that was an example of a condition hierarchy. This is a representation of how OHDSI creates these. I wouldn't dream of trying to decipher that. The drugs have hierarchies as well, that the people who do it know how to do the vocabularies. Procedures have hierarchies, and measurements have hierarchies. So there are a lot of hierarchies built in there. But the very good news is OHDSI has apps for those. So you don't have to query them. You don't have to know how all of them work. You just have to learn how to use the OHDSI tools. Katy is going to talk about Atlas and Analytics today. These rabbits over here, Rabbit in a Hat and White Rabbit, are tools for ETL that Claire's going to talk about later on. I did talk a little bit about Athena. That's this green one down there. I'm going to just talk a little bit, just show you a little example in a minute. So in Athena, instead of going to the Downloads tab, you go to the Search tab. You can search for anything in Athena in all of the vocabularies. And so if I want to search for I-71.9, which is my aortic aneurysm, I do come up, this will show me all of the ones I showed you before in the query, and which codes they are and what vocabularies. Well, I wanted, of course, the ICD-10, but I see that the concept is non-standard. So I can't use this number, but if in Athena I click on the link right here for the name, it will go to a details page. And some of these details pages are very, very large, but in this case it's just, this is a aortic aneurysm and dissection. When it says is a, that means it is, that is one of its ancestors. But then it also says this non-standard to standard map is aortic aneurysm 317585, which we have seen before. So, so you can find these details in Athena, and actually representation that I had with aortic aneurysm and showing the ancestors and descendants. I'm not a clinician. I don't know anything about aortic aneurysms, but I used Athena to fill in the details of that graphic. So it's here, being able to use. Atlas is another tool that Katy's going to talk about. The reason I'm showing it here is that you can select descendants of your, so for Cipro, you can find all the different descendants of Cipro. You can check that you want to see all of the descendants. You can uncheck some descendants. You might not want to see every descendant depending on what you're doing with your concept set. So that's just another example of a tool to use the hierarchy that you don't have to do yourself. And so that's it, whirlwind tour. I've got some additional links. Book of OHDSI has got, everyone should read the Book of OHDSI. Maybe not from start to finish. I think it's better if you read it when you need something from it. But common data model and creating the code mappings, very important. We have the entire CDM 5.4. So that's the current version. Lots of good information there. Data model conventions, some cool SQL scripts, and that ERD that I showed you before. I do want to make a mention of Eden Academy. It's an online service that you can go to. There's a link there. You do have to sign in and join, but it's free. And there's a bunch of tutorials on there, intro tutorials and tutorials on Hades. And then the proprietary mapping, again, I've got that custom concepts by Maxime. And then a couple of papers that have been, not papers, posters, mapping custom source codes to standard concepts, a comparison of those two approaches, source to concept map, concept relationship. And then Who Wants to Be a 2 Billionaire, a methodology for migrating from source to concept map to concept relationship. And with that, we can move on.
Okay, hello everyone. So nice to be here. So my name is Jason Law. So I'm going to, I and Yong. So we are going to talk about the characterization population level estimation and also patient level prediction in the next hour. So, so first of all, so these are the four modulars in the 4 boxes we're going to talk about. So you can see they are clinical characterization, patient level prediction, and population level estimation. So those are very classical and very well-established modulars by the OHDSI community. So on top of that, we are going to also add another modular called factory learning, so which is about how to integrate data with privacy. So we all know OHDSI is a collaborative consortium, and we involve a lot of data contributors and also clinicians. So we have the scientific questions, and we trying to use all the data to answer those questions, right? So, but one thing is that so the data comes with a privacy, and we may not be able to share the individual patient level across the site. So that's why we we add these modulars to the 3 other modulars. So a little bit of background about me and also Yong. So I first started to interact with OHDSI when I was a postdoc. That was like back in 2018. So Yong is expert in meta-analysis. So basically, meta-analysis is like you are trying to answer like a medical question. So you are going to pull out all the literatures and aggregating all those literatures. So, but when we're trying to do the observational studies, so we find that the meta-analysis have some of their limitations. So, and then we started to commit to the development of very novel statistical methods on how to integrate data from observational data from different sites. So that's why how we go to the OHDSI community, and we started to developing our method and publish papers. So for me myself, I think I have been published more than 10 papers, and that really helps me build my career, and even helped me get the job as my as a assistant professor in my now university. So it's really. It's really glad to be here to talk about our method development. So first of all, so I'm going to talk about the patient journey. So we all know OHDSI involves a lot of real-world data, which basically claims data and also EHR data. So these both of them actually involve the conditions and the drugs. Drug and procedures are kind of like a treatment doctors given to the patient, right? And then you have some measurement from the, let's say, lab test or something like that. So, so in this plot, you can see we have a baseline, which is called like the treatment initiation. But before that, we have, the diseases, like pre-existing diseases for the patients. And then after that, we have the follow-up time, which we are going to observe the outcomes, basically some kind of like adverse event or some outcomes, clinical outcomes out of the patients. So we have, as we said, we have actually 3 major questions to ask, right? So first one is which patient chose which treatment after diagnosis. That's kind of like the pattern of the data, and we call it the clinical characterization. And then the other question is one treatment more likely to lead to the outcome than an alternative? That's the population level estimation. And lastly, you want to answer the question that for a given patient or even a new patient come in, right? So based on what we observed, their pre-existing conditions and the treatment they've been receiving, so will this patient experience the outcome given the diagnostic and the treatment? So this is called patient level prediction. So we're going to talk about the first box, which is clinical characterization. So OHDSI's characterization framework defines several terms here. So first, the T is for target cohorts, and then S for subgroup cohorts, and then F for feature cohorts, and finally the TAR, time at risk, which is a time window we're going to observe the outcome. So so first, we're going to see like a case study, which is about the treatment pathways for several conditions. So this study uses characterize treatment pathways for type 2 diabetes, hypertension, and depression, right? So it uses 11 databases from 4 countries covering more than 250 million patients, which is really a lot. So this one, you can see we have this plot. And we have actually 3 layers of the circle, right? So the most inner circle actually represents the frequency of the treatment or the drugs of the first line. So, right, so the first drug the doctor will be given to the hypertension patients, right? So you can see here the hydrochlorothiazide, which is really mouthful. So this predominate as starting medication, more than 18%, but often paired with another active ingredient as combo, right? You can see here, this is hydrochlorothiazide, and then it combos with this one, which is lisinopril, right? Lisinopril more significantly as predominantly as the sole therapy, right? So you can see if you look at the here, right? So this one is also lisinopril as the first line therapy, right? And then it actually more frequently be given as the sole therapy. So basically, calculation gives us the full picture of what has happened and what is happening, providing a rich, comprehensive knowledge base about the healthcare practice. So a bigger picture, so the paper actually talks about type 2 diabetes, hypertension, and depression, right? And it also involves a bunch of different databases, right? So here, so CCAE is from United States database, and I believe CPRD is from UK, and GMDC, I believe it's from Japan. So you can see if you look into those, right, those different colors, they actually, presenting different patterns of the drug. The patient will be receiving, if you are in a different country. For example, if you are in the UK, so you'll probably be using metformin and then glycoside as the first and second line therapy for type 2 diabetes. So those will give you very informative, and you can see there are a lot of heterogeneity between different countries when you come to the drug use. So the second box we're going to talk about is the so-called patient level prediction. So basically, it's what will happen to me, so personalized prediction. So the OHDSI has this framework, the prediction problem. So first, you have the T0, which is like the baseline of, you are deciding the patient cohort you are going to study the prediction, right? And then you have observation window, which is often, like 1 year, 2 years before the T0, right? Among which you will be observing all the diagnosis, treatment, and also all the measurements of the patient. And then you're going to use them to predict the upcoming outcome here within a specific time interval, right? So usually the outcome will be defined as a binary, which means either is yes or no. Yes means it is observed in the observation window. The 0 means it is absent, right? So let's revisit the anchor study. So in the anchor study, we are going to do a little bit of change. So for example, let's just say we are FQ user have AA or AD within 6 days after initiation, right? So let's look at this cohort. And then the T becomes the FQ users, and the outcome O becomes AA or AD hospitalization, and the time window becomes within 6 days after the first prescription, right? So this is like the well-defined question. You could also change the T. Let's say you can change the T as FQ and also TMP and also CPH users. You can combine them together, that's okay. It's just like you are including the treatment of interest also into the prediction problem. So you could have different definition of the treatment, but basically you're going to define a baseline and then define a pre-existing condition window, and then define a follow-up window to observe the outcome, right? So the prediction pipeline, so basically you first have a labeled observation, a cohort of patients, and then you construct the 0-1 labeled outcomes. And then you're going to, for prediction, you're going to split them into the training set and the testing set. You're going to use the training set to learn the model, right? And then use the model to do prediction for the test set. So the reason why we do that is because we actually have a very large toolbox, like you can use statistical regression, you can use random forest, and all these different machine learning and even most cutting edge deep learning methods, AI methods to do prediction. So the method wise, there's really a lot of choice, right? So, but so when we are dealing millions of patients and also thousands of features, right? So you would easily get into the problem of overfitting. So that is to say that we want to use a data split for training and validation that we can have a good testing accuracy, right? So we are going to avoid the overfitting problem, right? So sometimes a model can behave very good for the training set, but may not be very good for the testing set, right? So we want to have a good testing accuracy so that we can have a fair comparison. So yeah, so the AutoSI also have a very established, pre-defined assessment and diagnostic tools for sensitivity, specificity, and ROC curve, and also the calibration plot when you are trying to extrapolate the prediction model into a new cohort of patients. So I will just briefly mention. So if you click on this, you will go to the OHDSI. So they have the apps, to basically to build the model and also the diagnose the model. So so next we'll be talking about the population level estimation, which is how or why it happens. So basically it's about the causal inference. So this will take a little bit more time. Specifically, we are going to use extensively the anchor study to illustrate the methods we'll be using here. So let's still revisiting the anchor study, right? So the anchor study, we have the target, which is FQ drug, and the comparator exposure is C, is other antibiotics, TMP or CPH for UTI treatment, and the outcome is the AA or AD hospitalization, and the time at risk is 60 days. So actually the so-called population level estimation is a big chunk of the all the OHDSI studies. So actually OHDSI developed the so-called legend, which is for large-scale evidence generation and evaluation across a network of databases, right? So if you go to the paper wrote by Martin Schumir at JAMIA 2020, so they actually summarize the legend, the 10 legend principles. So which I'm not going to cover all of them, but I do want to mention that some of them actually will be involved in this talk. So here, so you can see we have a systematic process, which means it is predefined, well established. We don't like do it, we don't change it by study, right? So we do it a pre-specified systematic process, and then we actually use the control questions to adjust for the systematical bias out of the observational study. We also do multiple databases, and also we want to maintain the data confidentiality, which means that we are not going to exchange the patient level data from across the sites. So okay, so this one is the pipeline of the legend, or the real-world evidence generation for the population level estimation. So which we will be more focusing on this box, right? So basically, we're going to analyze the designed choices and then diagnose the study. So here. So okay, so let's look at or read this paragraph coming out of the anchor study, which is the statistical analysis section, right? So you can see, well, there are actually 3 paragraphs here. So out of the first paragraph, you can identify some keywords here. So first, we're going to use Cox regression to obtain hazard ratio of the comparison. So because the outcome is actually the time to AA or AD after the initiation of the treatment, right? So it will be within the 60 days, but it will be like a time, right? Say 35 days or 44 days, right? So those time to event. So for those time to event, we're going to use Cox regression. And here in blue, I am highlighting the so-called propensity score with matching to obtain balance between the covariance of the compared cohort. So propensity score matching is basically the major idea of, we're trying to mimicking or emulating a randomized control trials when we are using the actual observational study. So it's called a propensity score. So, and then highlighted here in blue, so we are using the negative control outcome to adjust for systematic bias in the observation study. So the negative control outcomes, or NCOs, simply means those outcomes we know, we are pretty sure we know that they are not correlated with the drugs, right? So when we compare FQ versus TMP, so there are some outcomes we know definitely that not related to this. So when we use these kind of outcomes and then we redo the analysis, we are expected to see a null result, right? So like, when we call the hazard ratio, it should be 0, it should be 1, right? But because of we're using observational study, so we might have the systematic bias, right? And then we're kind of like doing all these negative controls, and then we are having a distribution of the background noise. And then when we conclude the actual the comparison, we are going to use the background noise to adjust for our final result. So this is the whole idea of the negative control. And finally, we are going to use the random effect meta-analysis to combine each site hazard ratio estimation into a single aggregated hazard ratio. But here it actually emphasizes that, so we'll use the other method referenced here to take into account the avoid bias due to small or zero counts. So yeah, I've already covered this. So, but basically, so we are going to talk into details about the systematic or diagnostic to assess the validity of those databases, right? So the first is called empirical equipoise. So the second is called covariate balance, and then the third is called systematic bias, or EAS. So let's talk about a little bit of the propensity score matching. So here, this one is directly from the paper, right? So you can see from the observational study cohort, so we extracted more than 4 million of FQ users and 2 million of TMP users. So they are certainly different cohort of patients, right? So let's say use an illustrative diagram here, right? So let's say the blue ones are FQ users, and then gray ones are TMP users, right? So they are different. So the size of the dot actually represents the so-called propensity score, right? So which basically is the probability of you taking the FQs versus the TMPs, right? Let's say that. So when we do propensity score matching, we want to have a subset of both of the two cohorts, right? So that their propensity score is similar or the same, right? You can see here, we're choosing a subset of FQ users and then a subset of TMP users so that their, the dot size can actually matches. In that way, we can have actually comparable cohort from both the FQ and the TMP users here, right? So you can see after the matching, we get almost 2 million of FQ users and the same numbers of TMP users, right? And then the next step is we're going to diagnosis to see if this matched cohort is actually valid for the next step. So the first diagnostic, we call it empirical equipoise, which is basically you're gonna compare the obtained preference score for the TMP versus FQ users, right? So here, so we define the equipoise as you're gonna have at least 20% of patients in both cohorts had a preference score between 0.3 and 0.7, right? So here is one example. If you use here TMP versus FQ in this database, right, you can see they actually pretty good overlapped here, right? So 91% are in equipoise, right? So that means, so this database is actually well balanced here. So bigger picture, you can see because we have 7 from the United States and 7 out of the United States, so we have 2 comparisons here, right? So you can see, generally speaking, most of the US databases have better equipoise than the out of United States databases, right? So, they are more varied here, right? But for US databases, they are actually a little bit better than this. But I think the conclusion for this diagnosis is that all the databases and all the comparisons actually passed this diagnosis, which means they all have more than 20% of patients in both cohorts had a preference score between 0.3 and 0.7. So next one is we're going to look into more details how the covariates will be balanced, right? So here is table 1, so showing that, let's say, the age distribution and the sex distribution. I don't list all of them, but just, a couple here. So I think the conclusion is that we have 12 or 9, sorry. So yeah, we have more than half of the databases actually passed this diagnostic. So here, the criterion is that one of the standard mean difference will be less than 0.1 after adjustment for all the covariates here. So this is the second diagnostic. The third diagnostic is called systematic bias, right? So as I explained, so the negative control outcomes are those outcomes that we know that are not related to the comparison, right? So not to the treatment and the controls here. So the so-called E's or the absolute expected value of the effect estimate is that look at this plot. So we have 50 negative control outcomes, right? So we can use all of these each individual negative control outcome to redo the analysis, right? And then you can have a distribution of the so-called background noise, right? So here we actually have a very good situation here. So which you can see here, out of 50, so there are 90% of the confidence interval that actually include one. One is a null, right, which is what we expected. So you can see most of the points here or NCOs here are actually showing no systematic bias. And if you, because so they have a very small null estimation. So if you calibrate them, it is actually becoming also very similar plots between these two because they are very close to the null distribution. So the criteria is that you will have a lower EASE score, which means less than 0.25. So that will indicate little to no systematic bias. So if you read this paragraph from the paper, so the range of EASE represented systematic bias was 0.03 to 0.15 in each of the 7 US databases for FQ versus TMP. And none of results from non-US database passed the EASE diagnostic, suggesting a high level of systematic bias. So for FQ versus CPH, so the EASE value were less than 0.25 from the 7 US databases and 2 Asian databases. So I think eventually we will have 7 databases that passes all the 3 diagnostics. So we will be using those databases for the final step, which is the, well, generally speaking, federal learning, which means, to do integrated analysis. So here, so this will be my last slide. So here, so you, for example, if you compare FQ versus TMP, you look at the figures 3, right? So this is a so-called forest plot. You can see from these 7 databases that pass the diagnostic, right? So they all give you, slightly different conclusions, right? So you need to aggregate them or integrate them or summarize them together, right? To obtain your final conclusion here, right? So which is, so the aggregated hazard ratio is 0.91 And the confidence interval actually includes 1, which means the p-value will be greater than 0.05, right? So that actually conclude you that there is no excessive risk of AA or AD when you taking FQ versus you taking TMP. So I think the similar results also applies to the FQ versus the CPH. So here I'm going to handle this to Dr. Yong Chen, so which we will be talking about a more cutting edge method in terms of when you are trying to integrate data from multiple sites when you have the privacy issues. So let's welcome Yong.
Good morning, everyone. Thank you, Jason, for the kind of introduction for the background. So now we are going to do federated data analysis. So I'm Yong Chen from University of Pennsylvania, Department of Biostatistics. So, so in general, people can always do some meta-analysis to combine results from different studies, right? That's something people are familiar with. But I'm going to try to give you some example and motivations about why we need a federated analysis. So for decentralized data like OHDSI collaboration, we know we have certain constraints that we cannot pull patient-level data. We can only communicate aggregated information. Those are two important constraints to keep in mind. And there are some other practical considerations. For example, in pharmacovigilance study, we are interested in the potential risk of adverse events, and those events are relatively rare, right? So for those rare events, it turns out that traditional meta-analysis can often fail because in some sites, some data partners database, there's no event at all. And there's something called a continuity correction, which has been proven to be introducing artificial biases. And there are some sites that have only 1 or 2 events. In those cases, actually, there are some artifact bias caused by such rareness of the outcomes. But in general, there are just better solutions than meta-analysis that we can do this multi-site data analysis. And now another way to think about the meta-analysis is, if you really think about the meta, what does meta mean? Meta means something post hoc, right? So it's usually, the traditional meta-analysis for clinical trial is that you can do some literature search about what has been already been done, and then you look into their paper and you extract the point estimate and the standard error. And then you are using a forest plot, visualize the data, and then combine them together. That's pretty rigid in the way that if you want those people to do something else, say, can you try this model, that model, usually it's not possible because the study is already completed, right? So, but the federated analysis, especially in the OHDSI consortia, as you can see, people are very collaborative, right? We have an opportunity to send out a customized protocol to tell people, say, can you do this and that? It's much more, less rigid compared to standard meta-analysis. I think if people just use traditional meta-analysis, like getting let different sites to run a logistic regression, combine the results, that's a missed opportunity because we can be more collaborative. So the goal is really like the following. Can we keep the analysis protocol as simple as a meta-analysis, just one round of communication, but we can still do better than traditional meta-analysis, right? That's the goal. Okay, so as I showed here, so beyond traditional meta-analysis, there are some really simple ideas. One of the ideas is that we can move towards something called a likelihood-based meta-analysis in a way that we can just share the entire likelihood function for some parameter that you're interested in. For example, hazard ratio comparing 2 treatments. And you can, in this framework, you can still apply the empirical calibration using negative control that Jason just described. So this will typically retain richer information. Just intuitively, if you see the entire likelihood function for hazard ratio versus a single point estimate and standard error, of course, the first option has more information, right? This is a paper that we published a couple of years ago, back in 2022. Exactly, this is particularly suitable for the case of pharmacovigilance, where when you have small or zero counts in those particular databases that you have in that particular cohort. So the key idea, again, is to directly approximate the shape of the per site log likelihood function rather than getting just a point estimate. You want to, and most of collaborators are comfortable sharing such information. So this is the result. So we actually had we can focus on column number 1 in the right panel. You can see that's one example that we considered. So we have 4 databases, CCAE and MDCD, MDCR, and the optimal database. And so for this particular example, we can create the likelihood function for the hazard ratio. That's the quantity you are interested in. And here, as I said, you can either communicate the entire likelihood function, or you can use some numerical trick to approximate that likelihood function. Then you can pull them together. So if you pay attention to the second column, example 2, in this right panel, and you can see that that's exactly the reason we avoid using the point estimate and the standard error to do traditional meta-analysis, because as you can see, the second column, the second row, MDCD database, you can see the likelihood function is flat at the top, right? So the hazard ratio would be close to 0. So that's, if you use the point estimate to summarize, the hazard ratio is 0, meaning that if you reduce the risk by 100%, right? How come that's possible? So basically, it's an artifact due to the rareness of the outcome. And on the other hand, if you look at the still second column, third row, you can see the likelihood function is monotonic. The hazard ratio is infinity, right? So you're jumping from a hazard ratio estimate of 0 to infinity from one database to a second database. It's really, really unstable. But the likelihood function really conveys all the information in the data. So that's a notion known as likelihood principle. So we are trying to combine the likelihood across these different databases. Then we can maximize that combined likelihood function. So that's the first use case study. So the second use case study is trying to take the advantage of the architecture of many collaboration. So for example, at UPenn, I'm going to launch say logistic regression model. I'm going to fit a logistic regression model, but I would like to get a model from multiple databases. I say I'm going to collaborate with Washington, St. Louis, Columbia, Stanford, just make it a multi-site study. Most of the time, when you reach out to your collaborator, the answer you get is, yes, we are willing to collaborate, but we cannot share patient-level data. We can share with you some aggregated data. So now this is an opportunity for you to design some smart algorithm better than meta-analysis, so that they can share some aggregated data, but you can get the result that's as precise as possible. So in this case, the operational flow is the following. Usually, we always need a study lead, right? Just like any multi-site study, you cannot say everyone is leading the study. There's too many chefs in the kitchen, right? So it's going to be a mess. So you need to specify someone to lead the study, and that person, in this case, has access to patient-level data. And then you use that site to develop the study protocol, test run the analysis, and you can, in the logistic regression example, you can get some parameter estimate using the local data, right? And then you can distribute this protocol to other places. So that's precisely this paper is about. This is an algorithm known as OHDSI, stands for one-shot distributed algorithm for logistic regression, developed by my former student Ray Duan, now at Harvard Biostatistics. So also this is a OHDSI collaboration that we used, a PEN database to demonstrate this multi-site logistic regression model. So the operation is the following. So using the local patient level data at UPenn, we fit a logistic regression model. You can play with your favorite, candidate model, settle down with some favorite, model with your model selection procedure, forward selection, backward selection, settle down with the model, and get your model coefficient. And then you broadcast those initial value to all the collaborators. And then your collaborator actually just need to do one thing and one thing only, which is calculate this quantity here. This is a quantity, technically it's a gradient of the log likelihood function, but it's basically the slope that you are getting from at this particular initial value. You ask for this slope information. And imagine if you are fitting a logistic regression model with 20 predictor, all you need from your collaborator is a 20 by 1 vector. That's it. Regardless how many millions of patients you can have 100 million patients in your database, but you only need 10 numbers. That's it. And then with that 10 numbers, share back to those the lead site. And the lead site will reconstruct a target function and then optimize this function, then get a final estimate. So this algorithm is very simple to run. I think there's some elegance in this design in the sense that, number one, the lead site is doing most of the work, right? Really, you minimize what your collaborating need to do. So in that sense, it's really scalable, right? So you're asking for your collaborator to run literally a few lines of the code, 3 lines of code in R. You can actually get this gradient calculated using their own data. That's number one. You minimize what your collaborator needs to do. The lead side is doing 90% of the work. That's how most of the collaboration should be, so minimize, your data partners' commitment. Second thing is that you give a lot of transparency. So your collaborator actually, we are going to be able to review and audit what type of data they are sharing. They are basically sharing 10 numbers, right? So, unless it's an extremely rare situation, in most of cases, this 10 number, in this, if you run a logistic regression model with 10 predictors, from 10 numbers calculated from millions of patients, that 10 number, we are not going to reveal the patient privacy. So you have a really good opportunity to reveal what you are sharing. So we actually, previously, we were running this study internationally, and there are some European sites had some concern about, what about sharing this 10 number? Because they actually keep all the digits, like 8 digits of decimals. And basically, we told them if you worry about those digits, that could be inverse engineered to hack some patient level information, you can always run it, right? So you can run it to first decimal or even integer, right? So, but again, the point is that you are sharing 10 number calculated from millions of patients. That's how different would that be compared to a standard table 1 in an epidemiological paper, right? So you allow people to audit what to be shared. And the third thing is that it's communication efficient. So I cannot emphasize more about the communication efficiency because the traditional approach was an approach developed by informaticians Lucilla at Yale, and they really deployed a pioneering algorithm called the GLOR, where you let the different data partners to iteratively change those estimates, and then basically do this iteratively to get some final results. But nowadays, with more awareness of the privacy, it's difficult to deploy this model to many hospitals, allowing hospitals to automatically exchange their estimate. So this is a so-called one-shot or one-round approach in the sense that you only need a collaborator to to do one round of communication. So there are some synchronization issue we avoid, right? Think about if we actually run some algorithm with 2 rounds of communication. First round, we have 40 data partners. We give them a month to give us the results. And by the deadline, actually, like 38 of them actually finished. Then we are facing the question, are we going to wait for the next 2, or are we going to job those data partners? Okay, and then when you get to all the results aggregated, you update your result, you have to run it again with the remaining 38 data partners. And then you have to wait till all of them finish, right? And one of the data partner from Europe, they really, in the summer, they write an automatic email saying, I'm taking a 3-month vacation, I'm not going to respond, right? So this human in the loop is actually a very important concept in federated analysis. We need to keep those data partner in mind. That's why we push our limit to make this federated learning as simple as possible. So if I'm doing a quick survey, for example, say we are running a multi-site study. So you have 2 options. Option 1, you can ask them, each data partner to run your code for 1 hour. But you need a 3 round of communication. Each round you have to wait for everyone finish, and then before proceeding to the second step. That's option number 1, 3 round of communication. Each time you only need to run 1 hour. Second option, you can let a computer to run for, say, 12 hours, but only 1 round of communication. So how many of you would prefer option 1? Can you raise your hand? So, and how many of you will prefer option 2? So I see lots of hands raised, right? So that's the point that a lot of times human time is more expensive than computing time, right? So we can let computer to do the work. Plus, this is not an expensive calculation. So the design of this OHDSI actually generalized to almost every single algorithms in our framework called the PDA, Privacy Preserving Distributed Algorithm, which is a suite of the algorithms, R package, including more than 30 algorithms for different tasks. So the key philosophy is to make the communication, to push the communication to 1 round. So in the case that you're curious what we are sharing, right? So this, suppose you are having, say, 4 data partners. You're asking the question, what are the risk factors of the acute MI, myocardial infarction? You fit a logistic regression model with 4 risk factors. And then you have 2 options. Option 1, for those of you working with multi-site study, you need to go through a very lengthy data usage agreement, IRB, to get all the data partners share patient-level data to you. Option 2 is running this OHDSI. Basically, you just need them to share 4 numbers. And I can show you in the next slide, for logistic regression model, the results are nearly identical. So this is actually the real data analysis result. We use the PEN database and we investigated a specific question, say, what are the association between medication use for women during pregnancy? We scanned actually 100 medication. For this 100 medication, what are the association between those medication use during pregnancy and their pregnancy outcome? In this case, it's a fetal loss, right? And we listed 4 options. The option 1 is we use only one of the PEN health system. We have 8 hospitals within the PEN medicine health system. We just used 1 hospital. So this guy is not going to collaborate, just using the local data. That's the first one, the light blue one. And then the green one is a gold standard. In this case, we can have all the 8 hospitals' data pooled in one database. So we just fit this logistic regression model on this pooled database. That's usually considered as a gold standard. And then we can have 2 versions of OHDSI. OHDSI 1 is a setting that we ask the data partner to share the P by 1 vector. So P is the number of predictors. And then OHDSI 2 is actually going beyond, say, can you actually share beyond this vector, it also share a p by p matrix. In this case, it's a 10 by 10 matrix. And as you can see here, first of all, the estimate using the estimate of the odds ratio using the local data, one hospital's data has a lot of variations, right? You can see that there's a lot of variations. And the green one here, we actually ranked these drugs, 100 drugs, by the pooled estimate. The green one is over there. But if you compare the two OHDSI estimator, the pink one and the purple one, they're actually very close. And over there, we actually zoom in to this particular arbitrary part. You can see the OHDSI2 is really on par, like nearly identical to the pooled estimate. And here we are talking about the medication with very different usage pattern. Some medications were used by 10% of pregnancy women, which means the data are not so unbalanced. Some medication were used by only 0.5% of the women during pregnancy. So even for very unbalanced comparison group, this OHDSI approach will be able to recover nearly losslessly to the pooled estimate. So this is really a strong voice, basically saying that, in those many cases, we can do so much better than meta-analysis by just designing a smarter protocol, right? And then the third example is a federated Cox model. We have a procedure called the OHDSI. So, logistic regression model and the Cox proportional hazard model, which is for time to event outcome, they are so popular in medical school. So I can bet for my 1 month's salary, someone at this moment is fitting one of the two models in pain medicine. So this is so really popular model. So we actually, for this model, it's actually a little bit trickier because there is something called a risk set, right? So risk set really means that in Cox proportional hazard model, you need to continuously update the risk set for those people who are still alive at risk, right? And then, so this actually entails a more complicated algorithm, but still it's a one-shot algorithm. So I'm going to show you the results. So we used the 4 databases that are commonly used in OHDSI for claims data, and we studied the risk factors associated with acute MI and also a stroke. And in this case, we actually compared the difference between what you get from meta-analysis and what you get from a federated analysis. So on the left panel, we listed the result from pooled data analysis. We actually have 4 databases at J&J pulled together. We can fit one single model on the pooled database. And then green one is a meta-analysis result. And then again, the blue one is the OHDSI, the federated analysis result. So as you can see here, the blue ones estimate are fairly close to the pooled estimate. And on the other hand, meta-analysis is fairly off, but even so, more so in 4 out of this 8 risk factor evaluation, the 4 of them circled by this red box, they are even qualitatively different compared to meta-analysis result. So meaning that your conclusion will be completely flipped. So like alcohol dependence in the gold standard analysis using pooled data was considered to be positively associated with acute MI. And this message was replicated by the federated analysis. You can see the blue one, which also has a confidence interval not covering 0. But the meta-analysis will give you a different conclusion, saying alcohol dependence has nothing to do with acute MI, right? So this really highlighted, again, the importance of using federated learning to avoid those misleading results. And you may be wondering exactly what type of data got communicated. So for the OHDSI, I showed you, if you are fitting model with 10 predictors, you just need to give 10 numbers. For the OHDSI, you need to share still aggregated data, but you need to share a slightly more complicated summary statistical table. So for more detail, you can refer to the paper published at JMIA. So we, over the years, we also developed a large number of algorithms going beyond ODEA and ODEC, but I still think the logistic regression model and the Cox model, they are most popular models in epidemiological studies. And in particular, we have an algorithm that I want to highlight. It's called ODEC-H, which H stands for heterogeneity. When you have the data from multiple data partners, usually there's no point to emphasize they all share the same baseline risk profile. So you should allow for some heterogeneity, say the study site at Spain and versus the study site at Korean. You allow them to have their site-specific baseline hazard function. And turns out that this ODEC accommodates such heterogeneity. And in terms of communication algorithm, it's much easier to implement. Again, you just need to share a 10 by 1 vector if you are fitting a model with 10 predictors. You don't need to deal with this more complex table anymore. So this is our software ecosystem. You can feel free to take a picture of this one. So we have a software package called PDA, well maintained over the years. And we also have a GitHub page, and we have a research website called PDA method.org. So, and this software interface is called PDA OTA. People actually can use this to share patient-level information. Exactly the opposite. Share the aggregated data using this PDA OTA. This OTA stands for over the air. So you are doing federated analysis over the air and by sharing those summary statistics. And this is basically a file managing system. This is like the interface. You have the step 1, setting up your data partners interface, and then step 2, you upload, review, audit, and upload your summary statistics. And this is a summary statistic that shared. I took a screenshot of what has been shared from Columbia Medical Center. So we were fitting, I think is a Cox model or some other related models. They are basically sharing a number of those simple numbers calculated from millions of patients. So at the end, this is again the principles we are setting for PDA: privacy preserving, accuracy, heterogeneity, communication, and implementation. So if you have any question about the implementation, feel free to reach out to me and Jason. So thank you.
Okay, you guys are doing a great job. This is a lot. It's okay if it feels like a lot. The point is now you've heard about negative controls and clinical equipoise, and you've heard about that the OHDSI vocabularies have hierarchies. That's just all you need to absorb at this point. So what I want you to do is we're taking a break until 10. I want everybody to go get some coffee or tea, bring back some energy into this room, at least go walk around for a few minutes because I feel like the energy is a little low. So bring back some energy, please, at 10 o'clock.
Okay, great. Thanks everybody for coming back from the break, re-energized. My name's Katy Sadowski. I'm on the real world evidence analytics team at Boehringer Ingelheim. And on my team, we're heavy users of the OHDSI open source analytic tools, and we also help to build and maintain them. It's really rewarding to be part of this community, so I'm super excited to be introducing you to OHDSI open source today. Here's our agenda for this session. First, I'm just going to do a quick introduction to the OHDSI open source tools. Then I'm going to talk a bit about what open source is and why it's important. And then the bulk of the time we'll spend doing deep dives on Atlas and Hades, which are the two most important pieces of software in OHDSI. So quickly, just to give you a visual of what we'll be covering in this section, I've got this diagram with a very high-level overview of the OHDSI open source ecosystem. A lot of the terms on here are going to be familiar from this morning's presentations. So we've got our OMOP CDM database here, where the actual data is stored. And then the usual entry point to interacting with the CDM is a tool called Atlas. We use Atlas to define study populations of interest, or cohorts, as we call them in OHDSI. And then we have Hades. Hades is really the workhorse of OHDSI open source analytics. Once we have our study cohorts built, we can use Hades to design and run studies using all of the methods we learned about earlier. characterization, estimation, prediction. And Hades is written in R, which is a statistical programming software. But under the hood, there's also quite a bit of Java and Python in the mix as well. As we've seen so far today, in OHDSI, we have some pretty strong beliefs about the way reliable evidence should be generated. And the beautiful thing is about this community, with Atlas and Hades, we give you all the tools that you need to uphold those principles yourselves. We make it easy to generate reliable evidence. And even better, these tools are all free and publicly available. How is that possible? Because all OHDSI software is open source. Open source software makes its source code free to access, use, modify, and redistribute. Often, as is the case in the OHDSI community, open source software is developed collaboratively by people across many different institutions. And these are generally people who either volunteer their own time or are paid by their institution to contribute to the project. I'll flag as well that this is a common and well-respected way of developing software. Lots of really widely used foundational software is open source. Python, R, Linux, Postgres, just to name a few. The technology industry today would look very different without open source software. All OHDSI software is freely available on GitHub, and as of last week, we had 351 different code repositories there. These range from mature software tools with thousands of users like Atlas and Hades to new experimental methods packages. The entire end-to-end process of running an observational study can be accomplished using OHDSI open source software, from mapping source data into the OMOP Common Data Model, to the CDM and the standardized vocabularies themselves, to performing data quality diagnostics, to building patient cohorts, and of course, to running a wide range of analytics from characterization to prediction. So this is probably a good time to flag that there is a lot more to OHDSI software than just Atlas and Hades. But in the interest of time today and to not overwhelm you too much, we're going to leave the rest out of scope. But this afternoon, there's going to be some advanced tutorials which go into a lot more detail than we'll cover today. Now I wanted to talk a bit more about why OHDSI software is open source and what an important role our software plays in the journey from data to evidence. The first thing is reproducibility. In order to consider a research study truly reproducible, other researchers must be able to do the exact same analysis that was done in the original study. And the best way to guarantee that this can happen is to share your analysis code, the line-by-line code that was used in that study. And the fact that all of OHDSI software is open source makes this possible. And we can not just reproduce the high-level functions that were run, but really the code that makes up those functions under the hood. So look at the network study model that we learned about earlier. This would not be possible if that study code was written on some proprietary analytics platform, unless all the participating institutions were paying to use that platform. These proprietary platforms, of which there are many out there, they're basically gatekeeping the ability to reproduce research to paying users. Second, related to reproducibility, if we want to increase the trust of the public and of regulators in observational research, being open about how we came to our conclusions is really essential, even more so today in the current climate. With OHDSI software, we can show what we did at every single step of the process. Third, OHDSI is on a mission to revolutionize the way that observational research is done. And we can only achieve this goal if we are working together across industries and across disciplines and inviting anyone who's interested to contribute to our work. Finally, OHDSI is all about large-scale research. And by making it free to participate in OHDSI and to use our tools, we're not just expanding access to these incredible resources, but also growing our potential to generate evidence at a really unprecedented scale. So now that I've set the scene, we're going to talk a bit more in depth about some of the most important OHDSI software tools. And the first one of those is going to be Atlas. Atlas is a web application used to design patient cohorts using code lists and logic relating to the OMOP CDM. First things first, what is a cohort? In OHDSI, we define a patient cohort as a set of persons who satisfy one or more inclusion criteria for a duration of time. On the slide here, we've got 3 example cohorts: pregnant women, children under 5, and men with HIV. And let's use these examples to break down that OHDSI definition of a cohort. In the labels here, we learn about the inclusion criteria persons need to satisfy to qualify for the cohort. So the first have to be women, and they have to be pregnant. The second have to be less than 5 years old. And the third must be men, and they must have a diagnosis of HIV. But in the image, we aren't told anything about when these patients enter and exit the cohort. What is the duration of time during which each person satisfies those inclusion criteria? Defining this time period for a cohort is super important for all of the methods we just learned about. For example, should the pregnant women enter the cohort at the start of pregnancy and leave at the end of the pregnancy? Should they re-enter if they get pregnant again or not? And do we care to follow them for any amount of time after birth? The answers to these questions are going to be super important for my study design. Children under 5 is actually even a better example. If I want to study, say, the incidence of influenza in this population, I need a consistent cohort entry date or index date for each child at which to start counting time at risk. That index date is a critical part of my cohort definition. If we don't have a standard way of defining both the inclusion criteria and that cohort entry event, we're opening the door for bias and error. And this is important both within a single study and across studies. In order to conduct reproducible research, we need to be very explicit and transparent about our cohort design choices. Fortunately, Atlas is a tool that allows us to do just that. So how does Atlas work? It essentially takes input from the user, defining their cohort, and turns that definition into a SQL query that can then be executed against an OMOP CDM. That SQL query is essentially going to output a set of rows with 4 columns: the cohort definition ID, a subject ID, cohort start date, and cohort end date. And that set of rows is your cohort. There's going to be 1 row for each time each patient enters the cohort. And the really nice thing about Atlas is you don't need to know SQL to use it, or any other programming language for that matter. So for this cohort design process, where we really need to be collaborating with study team members, clinicians, folks who may be not as technical, it's really nice that this tool is so accessible. So now I'm going to walk you through a few key features of Atlas. The first is the search feature, which lets you browse the OMOP vocabulary and choose concepts to use in your cohort definitions. You already learned all about the vocabulary from Roger earlier. You learned about standard concepts, source code, so I'm not going to rehash all of that. But I just so quickly here how you can search for a term. Here it's ciprofloxacin, a fluoroquinolone, and I get back a list of OMOP concepts that contain this term. The blue concepts here are standard concepts, and the red ones are non-standard concepts. And the count columns here are showing various ways of counting the number of records and distinct patients in the OMOP CDM with each concept. Very important detail in Atlas search, it is just a keyword search. So it's not going to pick up synonyms or related concepts. It's just going to return concepts that contain that search term, either in their name or in their source code. To demonstrate this, I'm going to show another example where I've searched just for an ICD-10 CM code, N39.0, which is a urinary tract infection code. And you can see here I've just gotten back 7 rows that have that exact N39.0 in their source code column. You can also see in this image all the ways that Atlas gives us to filter our search results. So on that sidebar, you can filter to a specific vocabulary or domain. We've also got another text search box to further refine our results on the upper right there. But of course, just searching for concepts isn't going to do anything permanent in Atlas. If I want to persist a set of concepts to use in my cohort definition, I need to build what's called a concept set. A concept set is a list of OMOP concepts used to represent a given clinical idea. So in the example here, we're building a concept set for systemic fluoroquinolones. The first thing to flag here is that Atlas allows us to use the vocabulary hierarchy to do this really efficiently. You actually already saw this image in Roger's talk earlier. So we can check this box for descendants, and that's going to give me all of the descendants in the vocabulary hierarchy of this concept ciprofloxacin. And we're also going to get for free all of those source codes that map into all of ciprofloxacin's descendants. So we're going to be able to get all of the different ways that that concept might be represented in a source database. So RX norm codes, NDC codes, et cetera. So if I want to build this concept set for fluoroquinolones, the high-level process is going to be first, I need to get a list of all the drug compounds in that class, like ciprofloxacin. Generally, we're going to work with clinicians to gather this sort of information. Second, I'm going to use the Atlas search feature to identify the top-level ingredient concept for each of these compounds, like the ciprofloxacin one you can see here, and we're going to add them to a concept set. Then we're going to select the descendants checkbox to get all the descendants of each ingredient. And finally, you can see one additional thing on this slide. We only want systemic fluoroquinolones for this study. So we've used the exclude functionality to exclude any formulations of these drugs that are not systemic. So in the screenshot, you can see we've excluded several ODIC preparations from our concept set, along with all of their descendants. So that's going to work the same way. Any code that could possibly be used for these local preparations of those drugs are going to be excluded from our concept set. The screenshot's cut off, but of course in this actual concept set, there's going to be a ton more concepts listed, more local preparations excluded, and then of course all of the different fluoroquinolones are going to be included here. Another thing, if you're following along on your laptop, the link at the bottom there will actually bring up OHDSI's demo Atlas instance, and you can see the whole concept set there yourself and browse around a little bit. So as we're preparing to define our cohort, we're going to go through this exercise of building a concept set for all of the relevant criteria in our cohort definition. In our example, I'd also be building a concept set for urinary tract infection. I'll go through a similar workflow, except I'm going to be using the condition hierarchy instead of the drug hierarchy here. And then we're going to bring it all together in a cohort definition. So in Atlas, the starting template for every cohort definition is exactly the same. And we're forced to specify a cohort entry event. That will become the cohort start date or index date for every patient in the cohort. We need to specify inclusion criteria, and we need to specify a cohort exit event. That's going to become the cohort end date or when each patient leaves the cohort. This way, we're going to be sure that every single one of our cohorts will comply with that important OHDSI definition, a set of persons who satisfy one or more inclusion criteria for a duration of time. And as such, these cohorts are going to contain all the necessary information to design a robust observational study. So in our example here, the cohort entry event is a drug exposure of systemic fluoroquinolones. You can see that we've loaded up the concept set for systemic fluoroquinolones in our cohort entry event right there. That's the same concept set I was showing you before. And something we've done here is we've selected to limit our initial events to all events per person. In this study, we're not just interested in the first time someone was exposed to fluoroquinolone, but all times they may have been exposed to that drug. And patients are going to enter the cohort at the start date of this drug exposure for the fluoroquinolone. That's going to be their index date. Another thing to point out here is we have not enforced any baseline or follow-up observation requirement, but in a study where you want to, for example, require patients to have some continuous observation before index to check for comorbidities, you could specify that here in your cohort entry event. And then we've got a couple inclusion criteria, which are all applied relative to the cohort entry event. This is a very important concept in Atlas. So in an Atlas cohort, everything is anchored around that starting time point at which a patient enters the cohort. So here, a patient potentially enters the cohort when they start a fluoroquinolone drug, but then we need to check that they meet all of the inclusion criteria relative to that start date. So first, did they have a urinary tract infection within 7 days prior to starting the drug? And again, you can see we've loaded up a concept set, this time for UTI, and we're telling Atlas, look for condition occurrences with any of the concepts in my UTI concept set, and see if those fall within 7 days on or before the start of the fluoroquinolone. If not, that drug exposure won't qualify for the cohort. And we've got a similar pattern for the second inclusion criterion on the list, which requires no hospitalization within 7 days of that fluoroquinolone exposure. This is another important Atlas Quirk 2 flag. We call all inclusion-exclusion criteria inclusion criteria. Essentially, we think of an exclusion just as a negative inclusion. And finally, it's not shown in this screenshot here, but we have a similar block as the cohort entry events for cohort exit criteria. So we've identified when patients enter the cohort, we've made sure each of those entries meets our inclusion criteria, and now we just need to define when the cohort exit should occur. In more traditional language, you might think of this as the end of follow-up. So I believe for this cohort, the cohort exit date was defined as the end of the fluoroquinolone exposure. And generally, this is done when we only want to assess for outcomes while the patient is taking that drug. There's also all sorts of cool stuff you can do at that cohort exit, like collapse nearby drug exposures into one episode, padding at the end of the final exposure, and things like this, but we don't have time to get into that today. So, and also, link at the bottom will take you to this cohort definition in the Atlas demo instance if you want to browse around yourself. So that was a bit of a crash course into what you can do with Atlas. There's a ton more that you can do in this tool. We just don't have time to get into it today, but building those cohort definitions is really the primary feature of Atlas. And I just want to bring it back to the number one thing I want everyone to take away from this session today, which is a cohort is a set of persons who satisfy one or more inclusion criteria for a duration of time. Actually, to liven it up a bit here, I'm going to have us all say that together out loud, all right? So on the count of 3, let's say this out loud together. 1, 2, 3. A cohort is a set of persons who satisfy one or more inclusion criteria for a duration of time. Great! So now that we've learned all about building cohorts, we're going to talk about all the things we can do with those cohorts in order to generate evidence. And that's what HADES is all about. HADES is the Health Analytics Data to Evidence Suite, and it's a collection of open source R packages for doing observational research using the OMOP CDM. HADES gives you all the tools you need to run the types of studies we learned about earlier, both within your own institution and across a federated network. Some important features of HADES are the tools place a big emphasis on diagnostics and calibration. So they not only generate results, but also allow you to objectively determine if those results can be relied upon or not. Second, it's designed for big data. As we all know, real-world data sets can be huge, and traditional statistical software often might perform operations in memory that are not up to the task of processing so much data. Fortunately, HADES has built-in functionality that helps it more efficiently store and access large data sets, so as a user, you don't really need to think or worry about that too much. And just like Atlas, HADES supports 11 different database platforms. And now I'm going to give you a whirlwind tour of everything that's in HADES. There's a lot more to it. This is a theme today that I'm going to talk about just in the session, but you can find everything online on the HADES GitHub repository. So first, HADES has sort of a bunch of auxiliary packages that facilitate the process of running an observational study. We've got Database Connector, which unsurprisingly sets up a database connection to any of those 11 supported database platforms. We have SQL Render. This is an absolutely critical package which translates SQL queries across all 11 of those database platforms. This is another task that would normally be extremely onerous, especially if you're working in a federated network, but HADES totally abstracts that away for users. You just don't need to think about it. We've got Feature Extraction, another somewhat obvious name. This package extracts features from a cohort to use in modeling. One really cool thing about feature extraction is that out of the box, you can use it to generate tens of thousands of features, basically one feature for every condition, drug, procedure, and other type of clinical event in your CDM. Andromeda, this is the tool I alluded to earlier that helps us run large-scale studies on big data. It essentially provides a more efficient way to access and store big data on disk instead of in memory. And lastly, we have Eunomia. This is more targeted at software developers, but it's super important. You can use Eunomia to spin up a mini synthetic OMOP CDM in SQLite in order to test your code. Now, here are the main analysis packages that will actually be generating the results for different types of studies. Under characterization, we've got packages for simple descriptive analysis, computing incidence rate, treatment patterns, things like this. For causal inference, we have the cohort method package. This gives you tools for building propensity score models and running a variety of comparative cohort designs. Cohort method is actually my very favorite HADES package because despite the complexity of everything it does, this package just works. And it's so powerful. So you remember those tens of thousands of features I mentioned earlier? Cohort method lets you run large-scale propensity score matching using all of those features, and all you have to do is call one function and specify a couple of parameters. It also gives you tons of beautiful diagnostics displays right out of the box. You saw a bunch of those on the slides earlier, and those are going to help you make smart choices about the soundness of your study design. I think cohort method really exemplifies this ethos of making it easy to generate reliable evidence. But it's not all about cohort method. HADES has a lot of options for doing self-controlled designs and, of course, for running prediction models. We've got a package for sort of regular machine learning prediction and deep learning as well. I admittedly know less about the prediction space, but as we've described before, this afternoon, there's advanced tutorials, I think actually on each 3 of these different analytic areas. And then finally, Hades gives us all the machinery to build and run an end-to-end study pipeline. And these tools are really designed with network studies in mind. So the inputs and outputs can be easily shared across institutions working in a federated model. Strategist is sort of the central framework for all of this. It's a package that generates and executes a JSON-based specification for an OHDSI study. And there's also some super useful tools which leverage R-Shiny to produce interactive results reports for Hades outputs. You can get a website like this, essentially out of the box for analytics run using Hades, and this is made especially easy if you use Strategist to build and run your study. So I'll do a bit of a deep dive on Strategist now because the Strategist framework is really essential for running a successful OHDSI network study. When we're coordinating a study across many different institutions, these 3 principles are extremely important if we want to ensure the study is being run in the same way across every single site. First is standardized input. So Strategist generates a specification document in JSON, which contains all of the information needed to run the study from end to end. The cohort definitions, all of the analysis code, and what order it needs to be run in, the versions of all the packages, everything's in there. Second is standardized execution. So anyone with an OMOP CDM and Hades can use Strategist to execute a study defined in this way. So Strategist isn't just generating that specification document, it also serves as an execution engine. And the third is standardized output. So all Hades analyses have a standard output format, and Strategist packages up those output files so the results can be easily shared and aggregated across sites. The Strategist specification document can contain any combination of Hades analyses. It's totally customizable. Hades packages are built to be very modular and interoperable, so we really have a ton of options for how to combine them to design our study. Our Lego bricks here give a few examples, with the purple bricks for characterization, orange for prediction, and green for estimation. And one package that actually didn't get mentioned yet, but is super important, is cohort generator. You can see at the bottom of every single one of these stacks here. And what cohort generator does is it essentially takes that SQL query that's built by Atlas and it runs it against the CDM to generate a patient cohort. While you can do that generation step in Atlas, for the purpose of a study, you really want your analytic pipeline to be fully self-contained. And the way we do this on my team is we still use Atlas to design our cohorts because that interface is just so friendly for searching the vocabulary and defining the cohort logic. But we use another tool called Web API to pull down the cohort specification from Atlas into our code repository. And then we can use cohort generator to build the cohort as part of the study pipeline. So how is Strategist used in practice? It can be used to keep studies organized just within a single institution with a single OMOP CDM. The study code here in the red box, that's the Strategist input, and the aggregate results are the Strategist output. That results viewer, that's what we saw a few slides back, is a nice R-Shiny website where the study results can be displayed. You can also use Strategist to run a study across multiple OMOP databases still in a single institution. So Strategist makes it really easy to define your study once, point it at each database you want to execute it against, and then compile the results. And of course, Strategist can be used across institutions. So the study code block is the same exact Strategist specification. The result CSVs are all in the same format. And of course, they're aggregated according to whatever privacy settings were agreed upon in this network study. And then we can compile everything in a single database to synthesize the evidence and present the study results in the way that you learned about earlier today. Here are just a couple of screenshots that show you what all of this looks like under the hood. These are from the actual fluoroquinolone study code, which was built in Strategist, and there's a link to the GitHub repository at the bottom of the slide there. And this is my last slide for Hades. If all of that sounded interesting to you and you're an R developer, we welcome you to get involved as a contributor. So all of this software, like I've been mentioning, is completely open source and it's being actively maintained by members of the community, like myself. Anyone can get involved, so if you're interested, just check out the Hades website, which is linked here, It's got a whole guide about how you can get involved, or of course, come talk to me afterwards. So in my last few slides, I wanted to highlight just a few of the many, many topics that we did not cover today, which I thought might be top of mind for some folks in the audience. First, if the idea of a point-and-click interface for designing cohorts is maybe repulsive to you, as it is to many in the community, don't worry, we have Caper. So Caper allows you to do everything you can do in Atlas, but by writing R code. And it's actually not only for people who are allergic to GUIs, but it's for anyone who wants to generate a ton of cohorts at scale. So for example, if you need to build a bunch of outcome cohorts that all have the same template, and you just need to stick in different concept sets, you can use Caper to write that block of code once, loop through your concept sets, and then generate dozens or even hundreds of cohorts. Next, what about data quality? So we've talked all about these fancy methods, but how do we even know the database we're using is okay? There are many packages in Odyssey for this purpose, like Data Quality Dashboard and Achilles. Those are measuring quality of an OMOP CDM as a whole. And we also have got cohort diagnostics, which measures quality at the cohort level. I myself am actually the maintainer of Data Quality Dashboard, like Erica mentioned earlier, and I definitely identify with the jealous girlfriend here. So if you are a fellow data quality enthusiast, please come chat with me. We're doing a ton of cool stuff to help improve and better understand data quality in OMOP. And finally, how about all the logistical tasks of actually setting up your code repository, writing documentation, launching analysis pipelines? We have a very useful package called Achilles, which can help with this. Basically what it does is it sets up a shell repository for you, and it has tons of functions that can help you get started writing your analysis plan, organizing your analysis tasks, and building the results website. It can work with strategists or without it, so it's super flexible to different study workflows. We use this for every single study that we run within my institution, both exploratory analyses and formal protocol studies. And that's it for me. On this slide, we have a lot more reading and videos that you can watch if you want to learn more about Atlas and Hades. And please come talk to me afterwards if you're interested in getting involved in our open source community.
Okay, hi everyone. My name is Nicole Pratt from University of South Australia. I always start these sessions with, don't blame me, it's the jet lag. So I've been here for a couple of days, but I should be fast asleep by this point, so bear with me. So it's actually, my honour, I guess, to be here at the end of those sessions to really bring it all together and show you the results that we were able to generate based on all of that fabulous work that has come before. So, we went through how to define cohorts, how to use the vocabulary, how to implement an analysis, how to use all of the packages that have so nicely been written by the Odyssey community to actually implement these studies. So right now, every single one of you sitting here is very lucky, right? We are very lucky to have the Odyssey community and the platforms that have been generated by all of these wonderful researchers and have made them open source for you all to use to generate the evidence, okay? And you don't need to understand everything that we've been through today. It's not a necessary requirement for you to be part of Odyssey. You don't need to understand everything. We are a community, and that means we have everyone in this room with all of their own unique abilities and their own unique experience that we can leverage and learn from to, create the evidence we need to improve healthcare. So don't be discouraged if you've not understood everything. Understand your bit and work together as a community to enhance our work collaboratively. Okay, so that was just my little spiel. So I'm going to go through the results of this study that we've been using throughout this morning's session. So let's wind back, a bit of a reminder about the study. We're looking at the risk of aortic aneurysm and dissection, and Erica told us about what that was, with the use of fluoroquinolones, these antibiotics that patients can take for certain types of infection. And we've done a retrospective multinational network cohort study, and you know exactly what that means now. You know what a retrospective multinational network study is. We asked data custodians across the world to run an analysis for us to answer a question that was important, and we were able to do that because of all of the research that had come before through the OHDSI community in terms of the technical details and so on. And we used this cohort study design that Jason talked about. Okay, so just again, a reminder, fluoroquinolones are these broad-spectrum antibiotics. They can treat lots of different infections, including the urinary tract infection, and this is what we're going to concentrate on today. Some of the background to this is that the fluoroquinolones are really, really effective medicines, and their use has been rising internationally. That's a good thing and also a bad thing. In some ways, these are very specific antibiotics, and there is this chance of, antibiotic resistance and so on. So it's really important that we use these medicines judiciously and really avoid some of those outcomes. They're really well tolerated, but there was a meta-analysis published back in 2020, and this was based on 5 observational post-market studies that suggested that fluoroquinolones actually doubled the risk of aortic diseases. Now, that's, you might think, a high risk, but if you think about it, the baseline risk is really low. So a doubling of a really low baseline risk still is tiny, but those outcomes are really, really significant and, can lead to death in these patients. So it's a really very low risk, but a really important risk to avoid if it really is true that there is a risk. So the reason this study was actually done, and if we wind all the way back, the FDA warned about this increased risk because of these observational studies, right? So there was a statement by the FDA suggesting, that caution should be used when prescribing these medicines because of the results of these observational studies. Okay, so we deliberately did this study to answer this question. And OHDSI as a community back in, I'm thinking 2023 maybe, asked for challenges from the community. What are the questions that we can work together to answer? And we put up our hand to do this study because Australia also took guidance from the international community, as it usually does, and suggested that there was also this increased risk, okay? And they called out these recent epidemiologic studies. Now, that's not a very common thing to do for a regulator to place a warning on an outcome based purely on observational studies. And you can understand why they would do this. There is no way that there would be an RCT to investigate this risk. It was an unknown risk. You would need millions of people to be able to have sufficient power to do this in a randomised controlled trial. And who would you include anyway if you wanted to actually investigate this? So it really is a place of observational research to answer this question. Okay, let's have a look at those 5 observational studies. So here was a meta-analysis that was published on these 5 studies back in 2020. They included in total 2.8 million people, but the quality of the evidence that underpinned that association was deemed as moderate. So when looking at the quality of those observational studies, the authors of the meta-analysis suggested that they probably, wasn't that strong evidence. There were inconsistencies in the study design or the way that these researchers actually approached the question. They used different comparators. They used different follow-up times. They included different patient populations in terms of patient age. And they stratified by individual fluoroquinolones, some of them, all of them, a couple of them, and so on. There was also problems with confounding by indication and surveillance bias. And if any of you here are new to observational research, you will know that this is the bane of our existence, and has been the topic of my whole career, confounding. Only one of those studies included an active comparator, so compared against another similar fluoroquinolone. So you can see there's lots of inconsistencies there. Now, what we did is went through, looked at those studies, but also looked at all the other studies that had been published since those 5 studies. And again, all of those studies, you can see here, all of those studies used different study designs. They were predominantly just in single countries, so single point estimates. So you remember Yong talked about the fact that a single estimate in a single database on its own, may not be as high quality as it potentially could be. The indication for the fluoroquinolone was often not specified, or there were multiple indications with varying severity. If you think about it, the antibiotics that were used can be used for lots of different things. I think Erica talked about the fact that, one indication is anthrax. That's very different than a urinary tract infection, which is also very different to, acute pneumonia or, severe pneumonia, which it also can be used for. So once you're starting to include lots of different clinical indications, you're automatically going to get some variation results. I talked about this, there was unspecified or different active comparators, and oftentimes there was no justification for which comparator was used. Is this really a sensible comparator to compare my fluoroquinolones against? In terms of other definitions like the outcomes and the exposures and covariate balance and so on, many of those studies looked at, a single outcome or the both combined. They were all defined differently. They used ICD-9 codes and, no standardization. Some of them looked at the PPV, or the positive predicted value, meaning how good is my detection of these outcome events. Some didn't. They used different risk windows. Covariate balance was, tested in various different ways. Sometimes we had propensity scores, sometimes we had disease risk match scores. We had a lot of different approaches to confounding adjustment. Clinical equipoise was never looked at in any of those studies. So they're those graphs that I think Jason showed us. And there was no addressing that systematic error using the negative control outcomes. Okay, so I'm going into a lot of detail about these problems, but this is what we have in many of our observational research studies, when individual researchers do an individual study on their own, make their own choices, and then the regulators are left to deal with the results of that and to try to make a policy decision. So we did this study back in 2023, I should say, and the results were presented at the OHDSI APAC conference in Australia. So Jack Janetsky is one of the lead authors of this study, and he presented the results at that symposium for the first time. Jack is a fabulous Titan Award winner from last year, actually, because of this study. And what we did at that study is we actually asked the audience, based on what I've just shown you in terms of the observational studies that underpinned this alert from the regulators, how confident were the people in the audience that the evidence is reliable and can be trusted? Okay, and we asked them to rate their confidence from 1 to 10, right? So I'm going to get everybody to stand up. Everybody stand up. Real quick. if you're pretty confident that fluoroquinolones are associated with aortic aneurysm and dissection, put your hands on your head. If you're not very confident, put your hands on your hip. Oh, no one's got their hands on their head. Excellent. Good. So that actually was a little bit different to what, you can all sit down now. That was a little bit different than what we had at the OHDSI Australia event. We actually had this distribution here, you see up on the top right. How confident are you that the prior evidence is reliable and can be trusted? We had some people saying they were pretty confident, and perhaps it wasn't presented in quite a biased way as I've presented it to you. But, you know, there was a mixture, right? We also asked at the same time, how confident are you that fluoroquinolones cause aortic aneurysm and dissection? And those of you in the audience, when you see the word cause, you should, freak out a little bit. Have you actually proven that these medicines cause a particular outcome? And you can see that the answers were around 50-50. You know, no one was willing to sort of place their bets on one way or the other. So we have an issue here. This is the result we got from our audience. In that audience were the Australian regulators, and the Australian regulators had to make a decision about whether or not to alert the community about this risk, which is a really important risk, but they only had those 5 observational studies to go on, and they had to make a decision, right? So none of you here were confident, yet the regulators still did publish that alert, okay? And I think that is a really key point that you need to take away from today. We need to produce evidence that is trustworthy, that people can make really important clinical decisions based on. We're not doing this just for fun. We're doing this to improve healthcare. And to improve healthcare, we have to improve confidence in the results we generate. And this is what we do as an OHDSI community. Okay, so I've put this back up. So Erica showed us this, schema of what we do here in OHDSI, how we have our individual building blocks. And because we have those individual building blocks, we can create a beautiful Lego. And we say Lego, not Lego. Anyway, so what I actually think is what we have right now in this clinical evidence based on those prior observational studies is really a figure that's not really well formed, okay? It uses lots of different databases. We saw that there were lots of studies in lots of different places across the world, but we had no systematic phenotyping, we had no systematic study design, we had no systematic methodology, and we had no standardised tools. Okay, so we got an answer, we got a result, we got a figure, but perhaps it was not the figure we needed had we performed our analysis using the building blocks specified in OHDSI. I'll just skip that. It's really just saying we have this really rare event. We need to have a consistent approach across the world to have enough power to actually show this result. Now, some of you may have already seen this diagram. I think perhaps Yong showed it or maybe Jason showed it, but we flipped it, okay? We flipped it and we said what we need to do in OHDSI or any observational research is to increase trust, okay? And we have a process for increasing trust. And that process of increasing trust starts from, data quality. It then includes the phenotype development and evaluation. It then looks at analysis reliability and evaluation. And once you pass all of those steps, then you have the joy of presenting your results. If you don't pass any of those steps, then you're out. Your analysis doesn't make it into the meta-analysis at the end. It is not reliable, and we don't use it to inform the evidence. So this little person is trying to characterise Sisyphus. And Sisyphus is a mythological figure who represents repetitive and laborious task of pushing a boulder up a hill. Okay, so we inverted this diagram to try to show you that you need to push this boulder up a hill in order to get reliable and trustworthy evidence. Okay, so we're here right now. We're doing a cohort study. We're doing a hard cohort study. We're doing population level effect estimation and trying to understand whether we have this causal effect or not. So our objective was to estimate the risk of aortic aneurysm and aortic dissection following fluoroquinolone exposure compared to other standard antibiotics for urinary tract infection. So what are we doing? Trying to fill the gaps in the evidence that we know about, okay? So we're trying to fill gaps left unanswered. Now I like to think about the hierarchy here as a little Lego figurine. So you need each of the little bits in order to produce the result. So let's go through all of those things for the particular study. So with the databases, we ended up with 14 different databases across 5 different countries that covered about 630 million people. So you can see already that that's a lot more than what would be possible in a randomised control trial and what was included in the 5 clinical studies. Here are all the different databases, some in the US, some in Taiwan, Korea, Japan, and Australia. Lots of different patient populations, some EHR data sets, some admin data sets, and so on. So lots of different data sets across the world that had all been translated to the OMOP Common Data Model. Then we developed the phenotypes. So we had these databases, we developed the phenotypes. I won't go through that all again. Roger has shown you some of that and how we used the hierarchies and the vocabularies to define these cohorts. If you want to see more detail about how these were created, there's some great tutorials that we developed as part of the SOS challenge. They're all online on the OHDSI website, so you can go through and see how Evan Minty, who created these outcome cohorts and validated those cohorts as well. So here's the study design. We used a new user cohort study. We included patients over 35 years old who initiated an antibiotic for urinary tract infection, who were in the outpatient setting. Okay, we didn't want patients who were really severe in hospital with an infection. They needed to be diagnosed with UTI in the outpatient setting. And we did that by excluding people who'd been in the hospital within the last 7 days before starting their antibiotic. The intervention was systematic fluoroquinolones. Comparators were trimethoprim and cephalosporin. Now, those were deliberately chosen because they are good comparators for the fluoroquinolones. A doctor could potentially choose one or the other, right? It's technically and medically appropriate comparator. Our outcome was hospitalisation for aortic dissection aneurysm, and then we had these 50 negative controls. Now, who knows what a negative control is? Yeah, a couple of people? Yep. Jason talked a little bit about these negative control outcomes, but it's something you'll hear a lot in OHDSI and perhaps over the course of your time here in the next couple of days. A negative control outcome is a really, really important concept when we're trying to understand systematic bias. So in this study, we used 50 negative controls with things like absence of the lung, right? A fall, foot drop, whatever that is, a victim of a traffic accident, okay? These are all outcomes that we believe have nothing to do with antibiotics, okay? These are particular antibiotics, fluoroquinolones. So when we do our analysis on these negative control outcomes, we expect not to see anything. When we compare fluoroquinolone and cephalosporin, when we implement the analysis, as we're doing for our main study, if we implement it, we should get a hazard ratio of 1, right? There's no reason why antibiotics would increase your risk of foot drop, whatever that is, compared to cephalosporin, okay? So we implement these experiments and ask whether our study design actually shows increased risk or not. And on average, do we have systematic bias, okay? If we do, then we have to account for that. And we can do that using calibration, which I'll talk about a bit later. So hopefully, do people kind of understand now what a negative control outcome is? It's an outcome we don't expect to be associated with either drug. So therefore, when we do our analysis, we should get a result of 1. Okay, makes sense? If we don't, we're in trouble. We have to account for that. All right. So we used a large-scale propensity score, using covariates measured at baseline, using regularized regression. And again, this is all part of the Hades package, implementing the propensity score. We did a matched analysis, so we matched patients on their propensity score using a 1-to-1 ratio. So somebody who had a propensity score highly likely to get the fluoroquinolone was matched to somebody who was also likely to get fluoroquinolones, but they actually got a cephalosporin. Okay, so those two people are very much similar in their propensity to get the treatment. It's just that one got the treatment and one didn't get the treatment. So they're a match. We used Cox proportional hazards model, time to event outcome, to model the outcome over several risk windows, but I'll just show you the 60-day for now. Okay, so we also employed these objective diagnostics that we heard about earlier this morning. So we made sure that we had covariate balance once we matched on our propensity scores. We ensured that we had clinical equipoise, meaning our propensity score distributions were sufficiently overlapped, okay, so that we had enough, patients to match to each other. We required there to be at least 20% of patients within a preference score of 0.3 to 0.7, okay, so sufficient overlap. And then we needed that systematic error that I talked about, so those implementations of the negative control outcomes. We wanted the systematic error to be low, okay, so that we didn't have this, lots of those negative control outcomes showing significant increases or decreases, okay. So we can test that using this ease score. All right, now to make it into the analysis, to make it into the meta-analysis, we needed each individual analysis for a particular outcome to pass all of those 3 objective diagnostics, okay? Everything needed to pass. If you failed one of those objective diagnostics, your analysis was not included in the meta-analysis. And then we did the pooling of the hazard ratios as Yong talked about. Now here's a bit, you've seen these before, just an example of one database and what the objective diagnostics looks like. So you can see in that first graph the covariate balance, all of the characteristics of our 2 groups, our treated group with the fluoroquinolones compared to, I think that's cephalosporin, perhaps, no, trimethoprim, sorry. They were very different. So our groups were very different to start with. Once we did our propensity score and we matched our patients, we had very little difference in our covariates. So you can see that on the left. We had great clinical equipoise and very little systematic error, meaning that many of those 50 negative control outcomes, when we tested them in this data set, most of them returned a null result, okay? The effect estimate was contained in a confidence interval that contained 1, okay? So you might also hear along the next couple of days this idea of effect estimate calibration. And what effect estimate calibration is, without going into too much detail, is we're trying to understand that systematic error in our negative control outcomes. If it's there, we want to calibrate all of our results back to a null distribution. Okay, so it's kind of like this measurement, calibrating a weight scale. Okay, you're trying to calibrate it back to null. I won't go into too much detail, but come and talk to me about it, or ask Martijn Schumi, who knows all about effect estimate calibration. Because we didn't have a lot of underlying systematic error in this study, our calibrated estimates were very close to the uncalibrated hazard ratio. Okay, so next is the standardized tools, the last block in our Lego man. We had these 14 different databases, and we could do this study because they were all standardized to the OMOP Common Data Model. And again, there's this, travel adapter scenario where we've got these different data sources, we implement the CDM on those different data sources, and now we have standardized data that speaks the same language. It doesn't matter if you're in Korea, it doesn't matter if you're in Taiwan, it doesn't matter if you're in Australia. Those databases all speak the same language because we use standardized vocabularies, so we can do this analysis quickly across these different data sets. We implemented the Strategos package to do this study, which uses all of those tools that are in Hades. And we then asked the participants to run that package in their data set behind their firewall and then produce for us the results. The single results that Yong talked about that were then provided to the coordinating centre for collation. The open executable source code is publicly available. Excuse me. You can just go to GitHub, and right now, if you have an OMOP data set and you want to run this study, you can do that. Okay, all of the code is available, and you can run the study to do this same thing in your data set and see how you go getting the results. Now, one of the things that we haven't really talked about a lot today, but it's something that is absolutely fundamental and critical in the studies we do, is that we have these building blocks that help us put together the little Lego man. But what we really want is the full instruction manual. And I've sort of picked this example because it shows the little men fighting. And that's kind of what the protocol does. It says, here's the building blocks to create your little Lego man, but here's all the bits you need to know how to play with those together. So the research protocol talks about, the study objective. It talks about, protection of privacy. It talks about, the underlying reason we're doing this study. It's all of the wraparound to all of those fundamental building blocks that we need to know how to get our little Lego men to fight with each other and play nicely. So that research protocol is actually available, so you can look at it and you can implement it yourself and really understand how we approached this study. Phew, now finally, we're at the results. Okay, but first, we need to make sure that we have passed all of our diagnostics. So you remember we talked about these 3 objective cohort diagnostics that we need to pass in order for the results to then make it through to the next stage of data collation. And when we did this, we had the fluoroquinolones versus trimethoprim. We had 7 databases that passed all 3 diagnoses. And you can see that the propensity score overlap, for example, did pass in all of the databases, but unfortunately, the awesome data set in Korea didn't pass on the covariate balance, okay? So it wasn't used in the final meta-analysis because there was something different about those 2 cohorts even after adjustment with the propensity score. So there was still some inherent bias in there, so it wasn't used, okay? When we did the fluoroquinolones versus the cephalosporins, 9 databases passed, right? So a few more databases, TMU, which is the Taiwan data set also passed with the cephalosporins, and I'll show you why later. Japan also passed. Okay, so we have 7 databases that passed for trimethoprim and 9 for the cephalosporins. I think you've seen this graph as well before, but what we end up getting is around 2 million patients in each of the cohorts, the treated and the comparator cohorts for the trimethoprim study, and then we had about 1.2 million in each of the cohorts for the cephalosporin. Okay, so big numbers of people after matching and past diagnosis, past objective diagnoses. Okay, and finally, here we are at the results. No difference. Okay, after all of this work, we identified that in the meta-analysis, there was no difference between our fluoroquinolones and trimethoprim in terms of our outcome, and the same for the use of cephalosporin as the comparator. So, after all that, no difference, which is very different than the 5 observational studies that the FDA, that TGA and EMA, other regulators around the world, use to issue the warning. Okay, so here we are with the biggest study we can potentially do, and we found no difference in the risk. So all of those results, I showed you one small section of the results, the overall, but if you want to look at any of the results for any of the analyses, for any of the databases, for any of the different sub-analyses, so we had different follow-up times. I just showed you the 60 days, but you can look at any of the follow-up times you like. You can look at all of the artifacts, all of the covariate balance, all of the individual covariates, and so on. It's all there. You need to go to data.odyssey.org, and you can see these results in a shiny app. For those of you new to Odyssey, go to data.odyssey.org. I can guarantee you can spend hours and days there looking at the results of all of the different studies that have been done across, the last couple of years in Odyssey. There are so many studies there with amazing data that you can look at, that you can interact with, that you can, investigate. You can, see how best practice Odyssey research works. It's hours and hours of entertainment. I love it. The other thing that is there are all of the legend results. So you'll hear the word legend a lot. I think we talked about it earlier today as well. The legend studies are really great examples of network studies and clinical applications of Odyssey work in the community. So there's Odyssey hypertension, which was the first legend study, and legend diabetes, which is the study, for those of you who were here last year, we had a lot of the results presented from the legend diabetes study as well. So that's all there. Now, I won't go through this. How are we going for time, Erica? We're good? Excellent. There are a lot of limitations, okay? So I've sort of given you a whirlwind tour of the results and showed you how fabulous the research process was, but there are still limitations, and it's really important to think about them when you're really trying to understand the results of your study. So the first limitation is that we had to restrict our study period to the end of 2019 to avoid the impact of COVID-19 on antibiotic changes or the use of antibiotics. So that's an issue, okay? And we all have that issue in the work we do in medication safety, is what do we do with COVID? So we had to restrict our data to that. There was also differences in the timing of the warning across the different countries. So we tried to limit our study to prior to the warning so that we didn't have that mucking up our results, but those warnings differed across countries and would have impacted the utilisation of some of those antibiotics. the definition of aortic aneurysm, aortic dissection, we had to use the ICD codes, and we did a really good job of the ICD codes, I think. But what we weren't able to do was look at imaging. So some data sets in the OHDSI community have really good data on imaging, some don't. We don't have, I don't know what tomography is, but apparently it's something you do to diagnose this condition, and that's not available across all of the different data sets. So there could be an issue with our definition there. But we did do a validation study in the Korean data set where we were able to actually manually review the discharge notes, and we had a very high positive predictive value. So we did a pretty good job of identifying the cases there. We already talked about this, the outcome rates are really low, but they were consistent with the known incidence of aortic aneurysm and dissection, which was really good. So we were able to verify that what we were finding in terms of the incidence was what we would be expecting based on just the natural incidence of this condition. But because they're low, we still had a bit of an issue with statistical power. Okay, I didn't show you those results, but we do also look at the minimally detectable difference, and we have a very, very rare outcome. So in some of the data sets, we just didn't have enough power. There is a bit of an issue with our generalizability. We only looked at urinary tract infection, but these medicines can be used for other diseases as well, so the pneumonias and so on. But we didn't look at those severe conditions, and we really only sort of wanted to restrict our analysis to those with UTI. Most of the results that passed the study diagnosis, and you might have picked this up, were from the US, okay? It may be that those are bigger data sets. It may be that there's different practices across the world, but most of those study diagnostics were passed in the US data sources, okay? And there is a reason for that. Let me show you. So I think maybe Jason showed you this. This is the propensity score distribution of the different comparator medications, right? So these are all the US databases, and you can see that the overlap between the fluoroquinolones and the trimethoprim are really, really nice, okay? They overlap really, really nicely. But when we look at the cephalosporin, which is the one on your right there, that's in the US databases as well, the overlap's not that great, yeah? Can you see that? So what that means is that the choice between your fluoroquinolone and trimethoprim is pretty even in the US, but there are very different populations who get the fluoroquinolones compared to the cephalosporins in the US. Can you see how that works, right? So that's in the US. If I now look at the Asian countries, or the countries outside of the US, you see a very different pattern, okay? The fluoroquinolone versus trimethoprim, those distributions are very much disjointed, okay? They don't overlap as nicely as in the US, but the cephalosporin and the fluoroquinolone graphs are much more overlapping. Can you see that? So this experiment really shows you how there are different prescribing practices across the world. And by doing these sorts of studies, we can start to unpack that, and we can really start to understand what's going on. But regardless of those differences, we still didn't find an increased risk of this outcome. We were able to adjust for those, selective prescribing practices in the different countries. So it's really important that when you implement these studies and you review the results, you look at these artifacts, like you look at the propensity score distributions to try to understand what's going on. You look at the covariate distributions and you try to understand what's going on, okay? Really important that you just don't look at the result, you look at everything and put it all together to try to understand what's going on. Right, so let's go back to our original question, whereas you're all very good students and said you didn't trust it anyway. But let's have a look what happened at the OHDSI Australia conference. So you remember we asked the question, how confident are you that fluoroquinolones cause aortic aneurysm? And we had this kind of, overall distribution that was sometimes, maybe not. So we remember back to the problems with our 5 cohort studies. If we now look at our results, and we presented this in the symposium, we said, okay, what if we just give you one database? What if we just show you the results of one of the databases, and and this was the result, and you tell me now how much do you trust this result? How confident are you that fluoroquinolones cause aortic aneurysm? Okay. With one database, the audience said, well, we're not really sure. There's still tremendous uncertainty. 95% of the studies we read are a single person study in a single database. Okay. So people weren't that sure, even though, the results are increased if you want to look at just the point estimate. So then we showed one more database and we said, well, what about this one? It's obviously a much bigger database, and you can tell that because the confidence intervals are much narrower. In this database, we also get non-significant results. Now, how confident are you that fluoroquinolones cause aortic aneurysm? And you can see that there's a shift in the distribution. People were like, okay, I've seen 2 databases now. I'm a little bit more likely to say that I'm confident. One was slightly underpowered, one was more powered but not suggestive of an increased risk. So it seems like maybe a bit more data in a single database tends to increase your confidence. So that's fine. Now, what about if we just show you our meta-analysis results? Now you can see that the distribution shifted a lot, right? There was a substantial shift, and it's collectively showing you consistent evidence of no effect. So these are quotes that people were writing down. So you can see that by presenting the results we have in this kind of meta-analysis, only using the results that pass the objective diagnostics, can really improve the confidence with which people interpret the results that we provide. So, what about trust? When we asked about how confident people were that this prior evidence, like the 5 observational studies, could be reliable and trusted, well, it was a bit all over the place. Once we presented all of our studies and our approach, we ended up getting this distribution. So pretty much everyone is now much more confident that the new OHDSI evidence is reliable and can be trusted, except this 9% of people here that were not all confident. And I can guarantee that they just misunderstood the question because they said, I thought you meant 10 was bad and 1 was good. So that was user error. So people actually were very confident that the results can be trusted. They were just, they just made a mistake. So in conclusion, the large-scale multinational multi-database study found that fluoroquinolones were not associated with an increased risk of aortic aneurysm and dissection compared to other common antibiotics in patients with urinary tract infection. A big mouthful to say we could not find an increased risk using the OHDSI approach. And in the paper, we suggested that the results do not support restricting fluoroquinolone use for urinary tract infections based on aortic risk alone. Okay, and it's really important that you sort of understand that nuance because there are other risks other than aortic aneurysm and dissection with fluoroquinolones, but we were just suggesting that that particular risk is not something that should really be part of the consideration for doctors in this instance. But there are other factors that should still guide use, and that's really important nuance. Now, lastly, The theme of the OHDSI Australia conference was all about consumers. It was about consuming evidence. Who do we generate our evidence for? Who do we want to consume that evidence? And if you think about it, when we consume anything, food, drinks, whatever it is, we want that food, drink to be palatable, right? We want it to appeal to the people that we want to buy that product. We want it to taste good, okay? We want it to do what it says on the package, right? We want it to be packaged in a way that people want to consume it. So we presented these results to the audience, and as I said, the regulators were there, but who was also there were the consumers themselves and the researchers. So we had a panel of patients, of consumers, clinicians, researchers, and regulators and policymakers, and we asked them, what do you think about this result? What will you do with these results? What the patients and consumers said is that, I don't understand a word you're talking about, right? That all of that was just mumbo jumbo. I don't know what you're talking about. Please tell me what it actually means for me or for my mum or for my daughter who needs to take this medication. So that's something that I think as a community we need to come together and work on, is how do we package these results to consumers. The clinicians, well, they wanted to know, well, what are the risks? What should I do for my patients? Like, how do I make a decision about what drug to give my patients? I understand you found no increased risk, that's great, but there are so many other risks. How do I then make that decision? So we as a community need to think about that. You know, it's not one outcome, it's a multitude of outcomes we need to look at. The regulators and policymakers said, well, okay, you found no increased risk, but we've got a warning out there. We're not going to take that warning away, right? So it's really important that we talk to our regulators early. We provide them really good high quality evidence so they don't make a decision based on that poor quality evidence and then have to deal with the problem of taking that warning away if it's disproved later. So I think we have some work to do in that space as well. And if you think about it, you know, another analogy, I love my analogies, a menu is like our protocol, okay? We need to describe what we're doing, we need to show people what are the ingredients, how they're put together, and how they should consume the evidence, or how the little Lego men should play together. So that's the end of Just on Time. Excellent, thank you.
Okay, you guys, we are on the home stretch. You have been a very polite class, but I want to emotionally prepare you. We cannot go to lunch unless some of you ask some questions after this section. So think about what you want to ask. This is the intro class, so no question is, too silly. Everything, this is a safe space. So, okay, so hopefully we said something today that sparked your interest. There was some part of today you're like, ooh, I could get involved with that. I'd like to know more about that. So how do you get involved with the OHDSI community? Okay, let me tell you a little bit about the community. We are always seeking collaborators. There is no bar to entry here. You don't have to pay any money. You don't have to write your thesis in OHDSI. If you are interested, you are welcome. And any type of individual is welcome. Whether you're excited about data standards or methodological research is really your jam, that's great. We need those people. Maybe you're just really excited about open source development. You like observational data and you like programming. There's plenty of opportunity here to do programming and contribute to the community. Maybe you just like asking questions like Nicole was just talking about, and you want to see answers and get answers to patients. All of these are great ways to get involved. And again, I want to stress, you don't have to know all the components. You can be really good at one or two things, and that's great. Also, you might just have a data set that you maybe you've converted to the common data model and you say, hey, I've got this data. I want people to use it to generate evidence, but I don't really want to create the questions. I don't want to design the studies. That's cool too. You can just have a data set. So there's many ways to participate. And I want to stress, you can give value by being an active collaborator, but you can also just be somebody who receives value from the community. You might need to get a set of questions answered, and you could reach out to the community, say like, hey, I don't really know how to go about this, but I know that patients need these answers, or hospitals need these answers. So you could just look to receive value from the community, and that's fine too. Okay, so how do we get started? The first thing is odyssey.org. Everything you need to know is on this website. And you can see I have a little orange box on the side. There is a new to OHDSI site. So this is all you need to know to figure out how to get part of the community. So what are some of the things on this website? First is the forums. And this is a great place for us to connect within the community. So hopefully all of you are old enough to know what forums are, but if you don't know what a forum is, it's basically just a place where you can post questions and people can post answers. And that's really what it is. So I would say if you're new to the community, you have questions, you can just go search the forums, because if you have that question, it's very likely that somebody has already asked that question. I'm very lucky that I'm part of a group at J&J that has a lot of OHDSI collaborators. So it's often in the hallway, we might have a conversation. I'll have a question, maybe Chris Knoll or Anthony Senna has an answer, and we'll say, okay, this was a good conversation. Let's go pretend to now have it on the forum so other people can learn from that, because not everybody's in the room together. So definitely scope out the forums. You can learn more there. I'd say maybe even slightly more important than the forums now, I would say, is our OHDSI MS Teams site. So this is where we go to collaborate. But even more than collaboration, I think if you have an account within Teams, you are able to get access to like when the meetings are happening, you can chat, you can see like different working groups going on. So I think the MS Teams has become very, very important. And your institution, you probably have an account with your institution through MS Teams. Some people are connected just through that account, but it's also possible to get an OHDSI specific account for you to connect a little bit better. You could also join our community calls or our work group calls. So the community calls happen every week. Now I will admit that the US call is a little US centric, so it's Tuesday at 11 Eastern Standard Time. But we recognize that that's horrible for some individuals in the world, like Nicole, who's on the other side of the planet. So we do record everything that happens during that Tuesday call. And there are lots of communities around the world. So there are, if let's say you are in an opposite time frame, there are other calls that are happening that might be better for you to join and participate. There are also work group calls, so depending on what you're interested in, maybe you're really excited about the common data model, you might join that work group. Those calls happen and they're recorded as well. You can learn about OHDSI in a bunch of different ways. A couple people have talked today about the Book of OHDSI. The Book of OHDSI, I think a couple years ago, maybe 5 years ago, we sat down to document a lot of this key information. So everything that we talked about today has chapters within the Book of OHDSI, plus a lot more that we didn't get to. The Book of OHDSI is available in soft copy online. You can actually just Google it and you'd find it. But if you're like me and you just like to hold the book, it is available on Amazon.com at cost. So it's not like OHDSI is making money here. I'm not pushing product here. But like if you want to have the physical book, you can do that as well. A couple of people today talked about the Eden Academy. There was an IMI project in Europe that converted a lot of data to the OMOP Common Data Model. And part of that project is they realized in order to be part of the community, you really need to be able to train and get some of that base information like we've covered here today. The Eden Academy is free to join. Anybody can go and create an account. And the classes are more structured like you would expect from a university, where there are sections and you can kind of work through at your own pace. Very similar content is available like we talked through today, but in greater depth. So for example, there's an OMOP CDM course that talks about the CDM and the vocabularies, and I think it's like a full day course, so like much more in depth. I actually think our YouTube is a great resource. So we like to record what we're doing, especially on those Tuesday calls. And so you can learn a lot. So let's say you want to learn more about Hades. You can actually just go to our YouTube site and say Hades and see lots of videos of people talking about it. One of the things that I really like that we do is these 10-minute segments. So a lot of our core things that we do have these short little videos. So highly recommend scoping out our YouTube. Every year at the OHDSI Symposium, we try to document what we've done in the past year. That's the Our Journey book. So there'll be an Our Journey book that will accompany tomorrow's talks, and you can kind of see like how the community has grown and what we've really focused on in the past year. But there's an Our Journey book for all the previous years, and those are all available online in soft copy. There is a newsletter that comes out, and so you can subscribe to that and get that kind of periodic update. I also think it's cute. Craig and Patrick do this like little podcasty thing. So if that's your jam and you like podcasts, you can listen to them drone on about whatever is like really kind of important in the community. And I think we do a fair job at our social media. So we have LinkedIn, X, Instagram, and Blue Sky. I know personally, I consume a lot of my OHDSI content on Instagram. You're going to see a lot of posters tomorrow throughout the year. Those posters get reshared, so you can actually see and become familiar with other people in the community and what they're doing. I think Nicole hinted about this earlier, but a lot of our studies, because they're open science, you are able to get access and start to see what other people are doing. So we have a GitHub repository that's specific to just studies only. And this little website here that I'm showing you actually kind of scrapes that GitHub repository and pulls together high-level information about what's going on. So for example, you could come out here, and I have an example highlighted. Chen he wanted to understand inflammatory bowel disease. So he put together a little package, he committed it to our GitHub studies repo, and in that package, he also included a protocol. So what he was looking to do is he wanted to understand irritable bowel, but he didn't want to just do it at his institution. He wanted to do it as many institutions as possible. So he came to the OHDSI call and he said, hey guys, I'm passionate about this. Please join my study. I was lucky enough to participate in this from Johnson & Johnson. We have a lot of different data sources. So I was able to go to that GitHub repo. I could get the protocol approved internally that we were allowed to run the study. I ran the study locally and contributed my data sets to this, the results from my data sets to this study. And this year it has been published. So this study, you can see it go all the way from idea to evidence generated. There's also the OHDSI Evidence Network. I don't think we've talked about this today, but one thing we realized a couple of years ago is that we had people who had data and we had people who had questions, and it was really hard to connect those individuals, especially if you don't know a lot of people in the community. Bridging that gap is hard. So we kind of created the Evidence Network. I kind of think of it like a dating app to get questions to data. And what we did here is any data partners that were interested in participating in network research would submit a summary of their data set. So there's a little program, you can run it on your data set, and it does a high-level characterization. So for example, it'll say, this database has 50 people exposed to fluoroquinolone. And then when people with questions come, and let's say they want to do a study on fluoroquinolones, the Evidence Network can say, okay, you want to do this study. I know about 5 databases that potentially could answer this question. And then like a dating app, they make a little connection. You as a data partner, if you are a data partner, you can choose whether or not you want to participate in the study. So everything's voluntary. The only thing we're trying to do here is connect people so that there is the opportunity to participate. So right now, our evidence network is growing. We are at 48 databases from 28 different data partners. Okay, we keep saying this today. This was a lot, and that's okay. And it's going to become even more intense tomorrow because a lot of this stuff we talked about today is going to be assumed that you've had exposure to some of these things. And you have, so you're going to be great. It's going to be fine. But what we'll do is we're going to have a help desk. So throughout the day, there are going to be segments of time where you're allowed to go off and look at posters. So it's kind of like you're not in your seat, you're out of the room. We will be sitting at right outside here. There's going to be a table that 2 of us at a time will be sitting there. So if you have a question and you just don't know what's going on, feel free to just come over and we can talk you through things. We can also connect you with individuals. So we want to continue to offer the support because it's going to be more drinking from the fire hose tomorrow. Okay, so we did it. You survived. And I emotionally prepared you. We now need to ask some questions. So I'm going to ask my fellow faculty members to come up here. And when people are asking questions, please at least wait for Mike. Come on, Katy, Roger, Jason, come on. You can do it. I believe in you. You have to stand. Okay, who? Oh, we have one. Yay!
I'm the big from AstraZeneca. Thank you so much. This was a very wonderfully planned introduction. It was a sequence. I learned a lot. There is one concern. There's one concern that my stakeholders usually point out, and I became aware of it. I got reminded about it when I looked at the fluoroquinolone example as well. And that is that whenever there is data cleaning and convert data mapping happening, especially in scenarios where signal to noise ratio is low, we might throw the baby along with the bathwater. And this is not exclusive to OMOP transformation, by the way, so in any scenario. How can I convince my stakeholders that with all the compromises that we made for this federated analysis, for example, OMOP is the best choice?
Okay, so if I were to parrot back your question, you're asking, is it specifically in the transformation to the CDM, or is it more in like doing federated network research?
Specifically in the CDM.
Okay, so the question is, when you transform to the CDM, do you have any loss along the way that you might end up augmenting your answer? So Roger, do you want to talk a little bit about this, or do you want me to take a crack at it? Oh, okay. So that is a valid question. So you can be concerned that when you go from your raw data to converting to the common data model, that maybe there's something that's lost there. But I would challenge that a little bit. So I'm a data girl, so I love data, and I did ETLs for a lot of years. And I would argue the act of transforming your data to the common data model allows you to actually interact with all of the data. If you're just doing one little study, you're really only touching little pieces of your data set. And it's not until you do an ETL that you actually know the outer parts. So you know that men are having babies, and that that there's somebody who's -30. You learn that when you do the ETL. So one thing I would argue is that by the act of doing the ETL, you actually learn more about your data. Also, we do a lot of data quality dashboarding. So in doing the transformation, we're doing a lot of characterization to try to understand, do things make sense? Data quality dashboard asks thousands of questions of your data to make sure, do things look like they're lining up? Not only from like just a raw data perspective, but also trying to expose what are potential issues just from doing the transformation. So if you're just using your raw data, you probably haven't done a lot of data quality. Through doing the transformation, you're starting to do that data quality. And then on top of that, I think we also do a lot of characterization of our data, so it helps expose. That's not to say that if you get to the point of doing the study like Nicole talked about, that's where you still need the people who are involved with the raw data to be around. So for example, in the study we talked about today, somebody could have run the study and said, hey, I have no fluoroquinolone exposures. This doesn't make sense. And that's why you need people who have the data say, okay, maybe I do have a problem in my ETL. Let me go back and kind of fix it. And sometimes that happens at the study phase, but we're doing a ton up front to mitigate that on the end. So I hope kind of answers your question. Do you want to go? Yeah, please.
There's another benefit to doing the network, the evidence network, because when you submit your statistics to it, then you get to see, compared to other systems, what they have that you don't have or what you have that they don't have. And so that can be a nice benchmarking check. Even if you never participate in any other networks, it gives you information back on the data that you've got.
Thank you. My name is Dimitri. I'm a data scientist at WC. I have a quick question. So in the antibiotic study, you did meta-analysis across the sites. And in the previous presentation, we learned that meta-analysis might not be the best way to configure it. So I want maybe a quick comment on that. So, and the second thing, maybe can you put into the perspective OHDSI and other research networks? So for example, I work with all of us. There is Epic Cosmos. So if patient level data is the gold standard, then those networks like Epic, they should have their own biases because they're vendor specific, but they still have this millions of participants in them. So, and one thing which I might have slight concern with OHDSI at the moment is how to get the data. So I work at MUC, I might get data from our institution, but how do I get any other data to make this study really reliable? So that seems to be maybe a difficult point.
Okay, great. So there's 3 questions in there.
Oh, sorry.
No, that's fine. The first question I think is going to be for Jason. That's about the meta-analysis. The second question was about different networks. And Roger, I'm going to pick on you again because you're a part of all of us. You could speak to that exactly. And then the last is about doing network-based studies and how do you actually engage that? So we'll start with Jason on the meta-analysis.
Yeah, that's actually a very good question. And I think I forgot to mention specifically that if you look into the paper, so they actually, so the so-called meta-analysis they are doing is actually a likelihood based. It's not only like doing, like a point estimate and then doing the first one. So it's actually beyond that. So what they cited is actually a paper Yong actually later mentioned. So it's actually like a recently published paper in 2022. So as I said, so it's a likelihood based. So they actually can mitigate much of the bias induced by the small or no, so showed in the Yong's slide that some of the slides actually sites that actually don't have any event of the outcome. So that is kind of like one of the most cutting edge methods we're putting there. And also if you go in beyond that, going to the more cutting edge federal learning methods, so we're actually developing a lot of methods, also doing kind of like a fitting to the OHDSI, this framework of doing propensity score matching and then doing the diagnosis and also the estimation. So there's a whole bunch of the pipelines and new methods here. Yeah, so I hope I answered your question, right? Yeah.
So what was your specific concern about like all of us?
Well, it's not that a concern. I just want to maybe put it into perspective. So is OHDSI a research network or not? And how does it compare to other research networks? And yeah, sorry. And data access, difficulty getting access to data was my concern about OHDSI.
Okay. All of Us is a network study. It came out before the OHDSI Evidence Network. We were my institution was part of All of Us, and we had to put it into the OMOP standard. So it's OHDSI and All of Us. Odyssey, or all of us didn't implement all of the Odyssey tools. They built their own tools. So yes, there's a lot of things in there, but I don't think you can use the standard data tools for that. And you mentioned Cosmos. We are in Cosmos. I don't do anything with it, so I can't give you any specific information about that. But it seems to me that's proprietary to Epic, and that's also not open. If you want to get more data, I think the Odyssey Evidence Network is the place to go and to ask if other people want to participate, and I think that would be your best bet.
Yeah, so Roger, definitely talked about it. So I think this is an area where Odyssey is still maturing, but I do think there's two kind of typical routes. If you have a question that you'd like to bring to the community, I think our evidence network is maturing, so you can definitely start with that. And you could say, this is my question. And then from there, the evidence network could say, based on your question, here are the data sets that you might be able to talk to. Doesn't mean that they're going to respond, but they might. Another way that historically within Odyssey people have gone about these larger network studies is to literally just bring it to the community. So we have that Tuesday community call. People just show up and they're like, I have a package, it's available, who wants to be my friend and run the package? So those are kind of the ways we've done it, but I would admit we're trying to get more mature in how we handle that.
Great session. This was amazing. Congratulations, Nicole and team, on the paper. That was amazing work. So I do have two questions kind of about some of the definitions in there. And, I should have begun with, I'm Grace Bellinger. I'm a postdoc at Johns Hopkins. I am not at all in pharmacoepidemiology, so sorry for my naivety. But this might be too in the weeds. Feel free to answer at a high level. But first of all, for the prescription of the antibiotics. From my understanding, some of the data sets were EHR and some were claims. So, and this is coming from a perspective, I've used Hopkins EHR and then Medicare claims, separate projects, not harmonized. But from my understanding, like, prescription is not equal to prescription filled, prescriptions picked up is not equal to medication adherence. So how do you, I know those of you in the field have to kind of like reconcile, like, come to terms with the fact that even though something was prescribed, even though something was picked up, doesn't necessarily mean it was taken. Yep. How do you control for that? And especially in the context of antibiotics, like from experience, I know that primary care providers, when you're doing UTI, STI screening, they'll prescribe something and they'll say if your lab comes back positive, pick it up. If not, don't. So that was for that definition. And then since there is a high fatality rate of aortic aneurysm and dissection, where does the death data show up? So if they don't even make it to Columbia Medical Center, which is one of the data sets, is there a cause of death autopsy showing up in claims? Or, given the severity of it, is it possible that an ICD-10 associated with aneurysm isn't even actually making it, even if though it caused death, because they didn't have time to collect that data? So feel free to answer those questions
this
at a high
is great.
level.
And Nicole, I think this might be one you might be able to take. So if I just parroting it back, different data sets have exposure, but just because they're standardized to the common data model doesn't mean that they're same type of exposure. And then secondly, where's the death data coming from?
Well, I'll start with the death data one because that's a bit easier. So the death data with it, we use the time to event analysis. So we censored patients at death if they had not had a hospitalization for aortic aneurysm dissection beforehand. So it was time to first event. So if they went to hospital with that diagnosis and then they died in hospital, they would have the event. If they died outside of hospital, then depending, I'd have to look back at whether or not we used the ICD code of the death as part of the outcome, but it would all be in the outcome cohort definition. I'd have to get back into that and see exactly what we did, and which is kind of the beauty of this research. You can go in and see exactly how we defined the outcome if that was your question. right? You can go in and have a look at it. I just can't remember off the top of my head what we did with that. So that's the death question sorted, I think. But we can talk more details later. The other question is, look, it's nothing magic about OHDSI that can help with the problem of whether or not a patient actually puts a tablet in their mouth and takes that tablet. We don't know that. In the claims databases, usually it's a supply date. If a patient actually goes to the pharmacy and gets the medication supplied, it's that one step closer to them actually taking the medicine. With prescribing, you know, there is that chance they won't even get it dispensed. So that is a problem. And, you know, I don't know if anyone else has ways they deal with it.
One thing we didn't cover in the slides today is OHDSI is really big on provenance. So in every event table, there's a type concept column where you actually can standardize the provenance of each record. So was it a prescription order? Was it a prescription fill? Was that on the medication list in the EHR? So if you do want to get down to that level of detail, you can, using all the standardized tools.
You're not free yet.
Any
Come on,
other
guys.
questions?
Any other
There's one at the back.
questions? You guys are very polite. It's very nice.
Hi, so I'm a little confused because you talked about creating your cohort with Atlas out of your OMOP data model. Do I need to load my entire analytics into the CDM before I do anything?
Yeah, that's a great question. So the question is, if I want to use a tool like Atlas, do I need the CDM? And I think, Katy, that will be a good question for you.
The answer to that is yes. So all the tools we described today work out of the box with an OMOP CDM, but that OMOP CDM is a prerequisite to using all these tools. Yeah.
So I have to load my entire data warehouse in there in order to find my cohort, basically.
You have to transform your data warehouse into OMOP. The data itself doesn't live in Atlas. Atlas connects to your database via an API. If you want to learn about how to do that transformation, there's actually a session I think Roger alluded to this afternoon where you'll learn all about that ETL process from source data into OMOP.
And then I have a follow-up question. You talked a lot about aggregate data. We do a lot of things based on community, right? So group of zip codes, et cetera. Is there anyone or has anyone had experience with sort of maintaining a quasi-patient level set of data but de-identifying it inside a CDM?
So the question is, if you have identifiable information and once you go to the CDM, which is going to be a research database, there sometimes needs to be this de-identification. There are people in the community who are really into this. And in fact, we talked about the book of OHDSI. One of the things that we've added, we're working on the next version of the book, we've added a small section about what does de-identification look like. I am not an expert in that, but there are people in the community who have ways to go about doing this, depending on whether it's the IDs or date shifting that you need to do. I'm just not an expert in that.
I just wanted to make one final point about the earlier question you had about, do I have to translate all of my data, my whole warehouse, into the CDM? There are certain, fields that must be entered, but not everything has to be entered. Everything you need for the study, yes, but not, imaging and everything. So there are certain fields and certain parts of the CDM that you must translate as a minimum, but it's not like you have to translate everything before you can do any of the analytics. Am I?
Yeah, no, that's
Right.
Yeah. Yeah, please.
OHDSI ideally, or OMOP ideally, should be use case driven. So you don't have to put everything in there. But if you're going to study measurements, you do have to have your measurements in there, and your conditions and your notes. And well, if you're not going to do notes right away, you don't have to do notes right away. You do those things, and what I've discovered is OMOP isn't a thing you do just once. And that's what, when I talk to IS departments, they think it's an extract like everything else, that you give them the thing, they give them all the code and they do it. It's an ever-evolving project. I think of it as like finding data for OMOP is like an archaeological dig. You get what you can off of the surface, and then you take care of that, and then you start scraping away at the surface and you find more and more and more. At a certain point, maybe you've got everything you need until it comes up with a study you want to do imaging. Well, now you have to start looking for imaging data. And so but like I said, having use cases for it is the best way to do it.
Okay, we have time. Oh, yeah. Yeah. No, we have time. We have 5 minutes.
Hi, I work for a company that facilitates and conducts EPI studies, and our clients often come to us to ask which data sets are fit for purpose for these studies. So I wondered if you all could speak briefly to what makes data sets more or less suitable to be transformed into OMOP. I know that, for example, oncology is still a work in progress. We have one client with a specialty burn data registry that they retrieve via a partially manual and partially automated EMR API. So what kinds of things would make you say, maybe you shouldn't transform that into OMOP before you do your study?
Yeah, that's a great question. So if I parrot it back, is it like what kinds of data lend themselves better to the OMOP common data model? I could take a crack at this, and if anybody else wants to add. So I think so I've been doing this for a long time. And over the years, I've seen a lot of different data sets lend themselves really well to the OMOP common data model. And then for us to have the ability to do analytics on top of that. I do think there is a little bit of a cost-benefit analysis that you have to do in your brain. So, for example, even at J&J, we are lucky enough that we are able to buy data. And sometimes we buy data that we know that we're just going to answer one question. That might not be a data set that's worth the effort in transforming to the common data model if we're just going to look at and try to answer one question. But if I have a data set that I know I'm going to use over and over and over again, it's worth the investment. I do think there are areas that we're maturing, like we've talked about today, things like imaging. There's definitely work that the OHDSI community is doing, and oncology as well. We are getting better, but because it's this collaborative community, as we learn about things that are not working so well, the CDM is not locked down. It's an ever-changing model. We have a process that we go through. So if you're a developer, don't worry. It's not like it's changing all the time. But we have the process to improve the CDM when we find something. But I will say we do fairly well, regardless of the type of data. Does anybody want to add a different perspective?
A kind of simple rule of thumb you could use is if your data set is not at the person level, your life's going to be a lot harder transforming that data into OMOP. So a tumor registry, for example, retinal data, where you have each eye, that's kind of a unique entity. It can be done, but there's going to be a lot more gymnastics you need to do to get that data into the CDM.
I was talking to Roger that this is actually a big question. So from my experience, so you see in the tutorial we have like the 3 boxes, right? So characterization, prediction, and population level estimation. So from my experience, I would say you probably need more, be more careful when you select those databases when you are doing the population level estimation, because of well, that's actually one part of the diagnosis, right? So after the diagnosis, you can see some of the databases does not pass the diagnosis because of they are having systematic bias, or you cannot match those covariates. So meaning that the preference of choosing different treatment for different databases actually sometimes is not even in some databases. So on the other hand, if you are prefer doing a prediction, I would say, so you want to be more inclusive of the databases, even though the two databases are far more different, right? So when we wrote the paper, we say it's called a heterogeneity. So even though your databases are very heterogeneous, so there is still a value of that bringing different data cohorts together. Because when you're building predictive model, you want the model to be, extrapolate to reach more patients, even though a new patient is far more different from the cohort. So yeah, so that's my experience. If you do estimation, so you want to be a little bit selective, and then if you want to do predictions, so you may want to be more inclusive. So yeah, thank you.
Okay, one more. I don't want to be in between you guys and lunch. That's a dangerous position to be in.
Hi, I'm Joe from Queen Mary University of London, and my question was, what are the main ways in which you guys are looking to get machine learning involved? So I work with a lot of machine learning PhDs, and they would love to have 600 million patient data, patients worth of data to do whatever on. Yeah, I guess my question is, what kind of things are you looking to use machine learning for?
That's a great question. So the question is, where are we doing machine learning within OHDSI? This is not my forte, and I'm hoping Jason can help. But I know, like, even just our like, once you consider well, no, I'm not even going to talk. Can you address that? I'm just not in this part of the community.
Okay, so I'll try my best. So as long as I know, machine learning is not being extensively used for the population level estimation. So it's more used in the prediction. As I showed in the slide, I have one slide that you have a large toolbox of, all these kind of machine learning, even, deep learning, AI, so these kind of techniques. So these could be easily, deployed or implemented as long as you get all the data cohort, patient cohort being defined and all the features being extracted, and then you can just apply whatever method you want. So, so there are some diagnostics, but that is beyond the OHDSI part. So, that's actually what if you learn machine learning, so all those diagnostics and in-sample, out-of-sample prediction. So those are things. So yeah, I think I hope that answered your question.
Nicole, we've got a question over here.
I just wanted to add one quick thing. Is you should go, if you're not already, go to Jenna's talk this afternoon. I think Jenna's doing it on patient-level prediction, and you'll learn a lot more about the machine learning methods. All right, this is definitely the last one.
Okay, really, really the last one.
Really last.
Don't be mad. Don't be mad. You guys are doing great.
I'm sorry, I'm going over the lunch break. I'm Manan Kamdar. I'm part of J&J. I'm a clinical scientist new to EPI, so sorry if it's a naive question. It's regarding the fluoroquine study. Given that the study focuses on short-term single-course treatment, what are your thoughts for the recurrent use of fluoroquinolone and how that would affect the study, analysis, and everything, especially being UTI is so recurrent, especially in elderly population, older females. So that's something as a clinical scientist, if I'm having this question, how would I design the study and analysis to answer that?
Yeah, that's a great question. I'm probably going to pass it to Nicole here. And it is about, in your life, you're probably going to have several courses of fluoroquinolone exposure. And if you're unfortunate, you might have several UTIs in your life. And so what does that do to your analysis?
Well, that's a very good question. And what we need to do is design that study together, right? So in our study, we only looked at first exposure. But you're right, there are multiple exposures per patient, and that's a standard problem we have in multiple exposure questions. That happens a lot, and the easy kind of way out is to just look at the first exposure, but there are methods that we need to develop for looking at recurrent exposures. I'm not sure if I've seen anyone do that in the Odyssey community, but we need to go and have a look at the odyssey.org to have a look at that. And that's a really great question. It's a good methodological question we need an answer to. So we need to work on that. It's a good clinical question. We need to get the clinicians together and see how often and how far apart those infections might need to be distinct events. You know, there's a whole heap of questions. So we have a new study. Anyone wants to work on this study? We can do that. But yeah, we only looked at first. Yeah.
Okay, you guys, you did it. You survived. And now you're prepared for tomorrow or whatever tutorial you're gonna go to this afternoon. So thank you very much. Give yourselves a round of applause. And we'll see you all soon.